Hello and welcome to Sleepy Science. What if nothing is the most misunderstood thing in the universe? What if empty space is not truly empty, but quietly filled with invisible fields, hidden energy, strange pressure, and tiny quantum activity beneath the silence? In this journey, we'll explore why the vacuum is not a blank stage, why particles may be ripples in unseen fields, why empty space can shape atoms and light, and why the quietest place in reality may still influence the fate of everything. These are not myths or science fiction ideas. They are real questions from quantum physics and cosmology, where nothing begins to look like one of the deepest structures in existence. So if you're ready to discover why emptiness may be far stranger than matter itself, tap like, hit subscribe, and drift with me into the hidden physics of the vacuum. Because the deeper we look into nothing, the more it seems that nothing was never truly empty. The strange problem of nothing in physics. You have never touched nothing, never seen nothing, never stood inside nothing. And this is where the problem begins, because the word feels simple until physics asks what it actually means. In ordinary life, nothing sounds like absence. An empty cup has nothing in it. A quiet room has nothing happening. A dark sky has nothing visible between the stars. But physics does not work with casual feelings. Physics asks a colder question. If you remove the air, remove the dust, remove the light, remove every particle, remove every sound, remove every object your hand could reach, what is left? At first, the answer seems obvious. Nothing. But then you notice something strange. There is still space. There is still distance. There is still the possibility that something could appear there, move there, be measured there. And if there is still space, is that truly nothing, or is it already a kind of stage? This is the strange problem of nothing in physics. The moment you try to describe it, you seem to give it structure. The moment you point to it, you make it into something. A perfect nothing would not simply be an empty box, because the box is something. It would not simply be darkness, because darkness is still a condition of vision. It would not simply be silence, because silence is what a listener calls the absence of sound. True, nothing would have no objects, no space, no time, no energy, no laws, no observer, no possibility waiting quietly in the background. And that kind of nothing is so difficult to think about that the mind almost slips away from it, like trying to hold water in an open hand. Physics has always struggled with this. Not because scientists are confused by simple words, but because nature rarely gives us the kind of emptiness our language imagines. When you remove things from a room, you do not remove the room. When you pump air out of a chamber, you do not remove the chamber's location in space. When you block light, you do not erase the rules that allow light to exist. Every time you subtract something, something deeper remains. This is why nothing becomes less like a blank and more like a question that keeps asking what counts as existence. Ancient thinkers wondered whether nothing could exist at all, because to speak of it seemed to turn it into a subject. Later, classical physics imagined empty space almost like a container, a silent background where objects could move if they happened to be present. But then Einstein changed the picture by showing that space and time are not just passive emptiness. They can bend, stretch, and respond to matter and energy. Suddenly, even the empty stage was not as simple as it seemed. Space itself had behavior. Time itself was part of the physical world. So the old dream of a clean, empty container began to fade. If the arena has properties, if it can curve, if it can change the motion of planets and light, then the arena is not nothing. It is part of reality, and this pushes the question deeper. Could there be no space at all? No time at all? But even saying before space, or outside time, quietly borrows the very ideas we are trying to remove. Before belongs to time, outside belongs to space. The language breaks in your hands. This is one reason nothing is not just a scientific problem, but a human one. Your brain evolved to understand things, places, changes, causes. It can imagine an empty field, an empty room, an empty night. But it struggles to imagine the absence of the field itself, the absence of the room itself, the absence of the night itself, the absence of the rules that would allow absence to mean anything. You can picture blackness, But blackness is not nothing. You can picture a void, but a void has shape in your imagination. You can picture infinite emptiness, but infinity is still a kind of structure. Absolute nothing is not a giant dark space. It is not a cosmic cave with no stars. It is not a blank screen waiting for the universe to begin. Those are images, and every image is already too much. The deeper truth is that physics can study empty space, low energy states, vacuum conditions, the absence of particles, and the behavior of fields, but absolute nothing may not be a physical object at all. It may be a limit of thought, a word pointing toward the edge where our concepts stop working. This does not make the question useless. It makes it powerful, because by asking what nothing is, you are forced to ask what something is. Does something exist only when it is made of matter? Then light creates trouble, because light is not matter in the ordinary sense. Does something exist only when it can be touched? Then gravity creates trouble, because you feel its effects without touching gravity itself. Does something exist only when it has a visible form? Then space, time, and physical laws become strange, because they shape everything while refusing to look like objects. The problem of nothing teaches you that reality is not made only of solid things sitting in a cosmic room. It is also made of relations, rules, possibilities, limits, and conditions. A universe is not just furniture. It is also the grammar that lets the furniture appear, move, change, and matter. And maybe this is why the question feels so haunting. If nothing is impossible to find, then existence may be more basic than absence. Maybe reality does not begin with a blank, then add things. Maybe blankness is already an idea that belongs inside a reality capable of having blanks. Maybe the deepest level is not a dark emptiness, but a framework that allows emptiness and fullness to be distinguished at all. That does not mean we know why there is something rather than nothing. We do not. Honest science does not pretend to answer what it has not answered, but it does show us why the question is harder than it sounds. The universe did not simply appear inside a normal empty room. The room itself, if we can even use that word, is part of what needs explaining. And when physicists talk about nothing, they often mean a very specific kind of physical emptiness, not the absolute absence philosophers imagine. That distinction matters. It protects us from easy myths. It reminds us that a scientific nothing may still have laws, structure, space, time, and measurable behavior, while absolute nothing would have none of these. So when someone says the universe came from nothing, the first question should be gentle but precise. What kind of nothing do you mean? A vacuum? A low energy state? No particles? No classical space? No time? No laws? Each answer leads to a different mystery, and each mystery teaches something real. It teaches that our everyday words are too small for the universe. It teaches that absence is not always simple. It teaches that the quietest idea in language can become one of the loudest questions in physics. And perhaps, as you sit here listening, the strangest part is not that nothing is hard to define, but that you exist at all as a mind capable of asking. You are made of matter, carried by time, held in space, shaped by laws you did not create, and yet you can turn your awareness toward the possibility of their absence. You can wonder what would remain if everything were taken away, and in that wondering, nothing becomes strangely full. Not full of particles, not full of light, not full of hidden magic, but full of meaning, because it reveals the outline of everything we usually ignore. The space around you, the time passing through you, the laws holding the world together, the fragile fact that there is a world to question. Maybe nothing is not a place we can visit. Maybe it is a mirror we hold up to existence, and when we look into it carefully, we do not find a blank. We find the quiet shock of being here at all. Why empty space is not the same as absolute nothing. The emptiest place you can imagine is still far too crowded to be called nothing. Picture yourself floating in the deepest darkness between galaxies, so far from stars that no planet warms you. No air surrounds you, no dust cloud thickens the view, and no human sound could ever travel to reach your ears. It feels like the perfect image of emptiness. Black, silent, open, almost sacred in its stillness. but physics would gently stop you there and say, not yet. This is empty space, not absolute nothing, and the difference is enormous. Empty space is still space. It has distance. It has direction. It has a before and after if time is still passing. It can be measured, crossed, curved, heated, cooled, stretched, and filled. Absolute nothing would not simply be a very large dark room with no furniture inside. It would be the absence of the room itself. No distance between one point and another, because there would be no points. No waiting, because there would be no time. No silence, because silence needs a world where sound could have happened but did not. No darkness, because darkness still belongs to vision and light. This is why the phrase empty space can trick the imagination. It sounds like nothing, but it is already something with a structure. Even the most carefully made vacuum on Earth, sealed inside a laboratory chamber and pumped until almost every molecule is removed, is not truly empty. A few atoms may remain. Light can pass through it. Gravity still acts across it. Instruments can still measure its size and temperature. It sits inside the universe, obeying the universe's rules. And outside Earth, where space seems more convincingly empty, the same lesson continues. Interplanetary space contains particles from the sun. Interstellar space contains thin gas, dust, magnetic influence, and radiation. Even the spaces between galaxy clusters, among the emptiest regions we know, are not pure absence. They are only unimaginably sparse. That word matters. Sparse, not nothing. Empty, not non-existent. When you look up at the night sky and see the black gaps between stars, you are not seeing absolute nothing. You are seeing distance filled so lightly that your senses mistake it for absence. The universe is very good at hiding its thinness. A room can feel empty if no one is inside it, but the air is still there, the floor is still there, the shape of the room is still there, and the laws that let you call it a room are still there. Space works in a similar way, only on a scale that makes the mind quiet. The gap between two stars may contain less matter than any vacuum we can easily create, but it still has location. It still has geometry. It still allows light to travel through it. It still carries traces of events that happened long ago. In fact, one of the most important clues about the early universe, the cosmic microwave background, reaches us through space as a faint leftover glow from a much hotter past. That glow is not mystical, and it is not visible to your eyes as ordinary light, but it reminds us that what looks empty may still carry history. Empty space is not a blank page. It is more like a page written in ink too faint for the human senses, but not too faint for careful instruments. Absolute nothing would have no page at all. This distinction becomes important because people often use the word nothing too loosely, especially when talking about the universe. If someone says there is nothing in a box, they usually mean there is no useful object inside. If a physicist says a region is empty, they may mean there are no particles of a certain kind, or no matter dense enough to matter for the experiment. But neither of those is absolute nothing. They are practical forms of emptiness. They are useful simplifications. They help us think, calculate, and test, but they are not the total absence of reality. A vacuum is not a philosophical void. It is a physical condition. It can have pressure lower than the air outside. It can allow beams of particles to move without bumping into much. It can help preserve delicate experiments from contamination. It can be engineered, improved, and measured. And anything that can be engineered, improved, and measured is not nothing. It belongs to the world. Absolute nothing, if such a thing can even be meaningfully described, would not have a pressure, a temperature, a volume, a boundary, or a waiting potential. It would not be cold, because cold is a state of something. It would not be black, because black is an experience inside a universe where light and eyes can exist. It would not be lonely, because loneliness belongs to minds. It would not be empty in the ordinary sense, because emptiness itself usually means a space where something is missing. Without space, even missingness loses its place to stand. This is where the idea becomes almost impossible to hold. Your mind wants to imagine nothing as a scene, a black ocean, a silent chamber, an infinite blank. But every scene smuggles something in. It gives nothing a shape, a mood, a background. Physics teaches a quieter discipline. to ask what remains in the definition. If space remains, it is not absolute nothing. If time remains, it is not absolute nothing. If laws remain, it is not absolute nothing. If there is a measurable condition, it is not absolute nothing. This does not mean empty space is unimportant. In many ways, it is one of the most important things in physics, because it shows that the universe is not only made of visible objects. The spaces between things are part of how reality works. They allow motion, they separate stars, they carry signals, they give structure to the cosmic story. But absolute nothing is different. It is not a place between things. It is not the deepest darkness beyond the last galaxy. It is not outer space with everything removed. It is the absence of the very framework that makes between, beyond, and removed meaningful. And that is why the difference matters so much. When you understand it, the universe stops feeling like a collection of objects floating inside a dead emptiness. It begins to feel like an interconnected condition, where even the gaps are part of the design. The silence between notes is still part of the music. The pause between breaths is still part of being alive. The darkness between stars is still part of the cosmos. Empty space is not absolute nothing because it still participates. It still lets things happen. It still holds distance open. It still belongs to reality. And maybe that is the quiet lesson hidden inside this distinction. What looks absent may still be deeply present, and what we casually call nothing may be one of the most misunderstood somethings in the universe. So the next time you see a dark sky, or stand in a quiet room, or imagine the vast spaces between galaxies, do not think of them as pure nothingness. Think of them as the soft architecture of existence itself, nearly empty but not erased, silent but not meaningless, open but not gone. Absolute nothing is not the emptiest place in the universe. It is the absence of a universe where places can exist at all. The vacuum is not blank. It has fields everywhere. If you could remove every particle from a region of space and then somehow listen more deeply than human senses allow, you would not hear true silence, but the quiet presence of fields still spread through the darkness. This is one of the most important shifts in modern physics. The vacuum is not a blank background waiting for matter to arrive. It is not like an empty stage before the actors walk on. It is more like the invisible system that makes the actors possible in the first place. In older ways of imagining the universe, we picture space as a container and particles as tiny objects placed inside it, like dust floating in a room. But the deeper picture is stranger and more beautiful. According to quantum field theory, the basic ingredients of reality are not little hard dots moving through emptiness. They are fields that exist everywhere, and what we call particles are localized excitations of those fields, like small disturbances appearing in something much larger. An electron is not simply a tiny bead traveling through a void. It is a ripple of the electron field. A photon, the particle of light, is a ripple of the electromagnetic field. Other particles belong to their own fields too. The fields are not made of ordinary material in the way a table or stone is material, and they are not visible substances spread like fog. They are physical systems with values, rules, and measurable effects. They fill the universe in a way that feels almost impossible to picture, because your eyes are trained to notice objects, not the deeper conditions that allow objects to exist. Think of temperature in a room. You cannot see temperature as a thing sitting in the air, but every point in the room can have a temperature. Think of a magnetic field around a magnet. You may not see the field directly, but iron filings reveal its shape, and a compass responds to it. Fields in physics are more fundamental and more precise than these everyday examples, but the idea helps. A field is something that can have a presence across space, even where no solid object appears. The vacuum, then, is not empty because the fields are still there. Even when no particles are present, the underlying fields remain, and they define what kinds of particles can exist, how they behave, and how they interact. This means the universe is not built like a collection of separate things thrown into nothingness. It is more like a vast layered fabric of invisible activity, where visible matter is only the crest of deeper waves. The chair beneath you, the light reaching your eyes, the atoms in your skin, the warmth in your hands, all of it depends on fields that do not announce themselves to ordinary perception. You live inside them the way a fish lives inside water, except the comparison is still too simple, because these fields are not a fluid surrounding objects. They are part of what objects are. This is why the vacuum matters so much. If you take away every particle, you have not taken away the possibility of particles. The fields remain capable of being excited. They are like instruments that may be quiet for a moment, but whose strings still exist, still tuned by the laws of nature. A quiet violin is not the same as no violin. In the same way, a region with no particles is not the same as no fields. And when physicists describe particles as excitations, they are not using poetry to make science sound dramatic. They are describing a real and tested framework that has produced some of the most accurate predictions ever made. The electromagnetic field explains light and electricity. The electron field helps explain the behavior of matter. The Higgs field is connected to why many particles have mass. These are not decorations added to physics because they sound mysterious. They are part of the machinery of modern science. Yet there is something deeply humbling about this, because it means the world you see is not the deepest layer of the world that exists. Your senses show you shapes, colors, textures, and motion, but beneath that familiar surface is a quieter order made of fields interacting. When two electrons repel each other, it is not because tiny solid balls are angrily pushing in the way your hands push against a wall. It is because the fields and forces involved follow rules that produce that behavior. When light crosses space, it is not a marble flying through a dark tunnel. It is an excitation of a field traveling according to the structure of nature. When matter holds together, when atoms form, when chemistry becomes possible, fields are involved at every step. This does not make everyday reality fake. It makes it deeper. A wave on the ocean is real, even if it is not separate from the water beneath it. A song is real, even if it is not separate from vibrating air and listening ears. In the same way, particles are real, but they may not be the final layer. They may be the visible grammar of something more continuous, more spread out, more quietly present. And this changes how you think about emptiness. The dark gap between objects is not a dead nothing. It is filled with the same kinds of fundamental fields that underlie matter itself. You cannot scoop them up in your hand. You cannot photograph them like a mountain. But every experiment that confirms the behavior of particles is also, in a sense, revealing the fields behind them. The vacuum is not blank because the universe does not need visible objects in order to have structure. It has structure already in the rules and fields that remain when the objects fade from view. And perhaps this is why the idea feels both scientific and strangely personal. You spend so much of life noticing only what becomes loud enough to appear. The spoken word, the visible face, the finished action, the bright event. But beneath every visible moment there are quieter conditions that made it possible, hidden tensions, patterns, histories, and potentials. Physics tells a similar story about reality itself. What appears empty may be carrying the deepest order. What looks silent may be full of capacity. What seems blank may be the very thing from which appearance becomes possible. So when you imagine the vacuum, do not imagine a useless emptiness. Imagine a universe with its lights dimmed, its particles quiet, but its fields still everywhere, patient and unseen, holding the rules by which stars can burn, atoms can form, light can travel. And you can exist long enough to wonder why the darkness was never truly blank. Quantum fields fill space, even when particles are gone. Erase every particle from a region of space, and physics says you have not erased the thing that makes particles possible. This is the quiet, difficult idea at the heart of quantum fields. Particles can disappear from a place, but the fields they belong to do not vanish with them. Your ordinary imagination wants the universe to work like a room full of objects. Take the objects away, and the room becomes empty. Remove the dust, the air, the light, the atoms, and you imagine a clean blankness left behind. But modern physics asks you to look one layer deeper. It says that what we call particles are not independent little beads placed into space from outside. They are special states of underlying fields that extend through space itself. So when a particle is gone, it is more like a note ending in a musical instrument than the instrument being destroyed. The note stops. The instrument remains. And this is where the vacuum becomes stranger than ordinary emptiness, because it is not a graveyard where particles used to be. It is the condition in which fields are still present, but not producing detectable particles in the way our instruments would label as matter. To understand this clearly, imagine a calm lake at dawn. No visible waves cross its surface, nothing splashes, nothing breaks the stillness. But the lake has not ceased to exist just because no wave is rising. Its surface is still there, capable of carrying waves if disturbed. In a very loose and limited way, this helps point toward the idea of a quantum field. The electron field does not need an electron sitting in front of you to be part of reality. The electromagnetic field does not need a visible beam of light crossing the room to be present. The fields are the deeper systems, and particles are the events that appear when those systems are excited in particular ways. This is not just a poetic rearrangement of words. It is part of the framework behind the most successful descriptions of matter, light, and particle behavior. When experiments create or destroy particles, physicists are not watching tiny permanent objects pop in and out like magic toys. They are watching energy and interactions change the state of fields. In particle accelerators, for example, collisions can produce new particles because the energy involved can excite fields that were already part of the physical picture. The particles did not come from a hidden storage box inside the vacuum. They are expressions of fields whose possibilities were already written into the structure of nature. This also means that a particle is not always best imagined as a tiny, solid object traveling along a neat path like a miniature planet. In quantum physics, that picture can be useful in some situations, but it becomes misleading if you treat it as the deepest truth. A particle is more like a localized occurrence, a concentrated pattern, a measurable excitation. It can be detected at a place, leave a mark in an instrument, transfer energy, and behave with particle-like clarity under the right conditions. But beneath that appearance is the field, spread wider than the event you observe. This is why the phrase "particles are gone" needs care. Gone from detection does not mean gone from reality's underlying capacity. A room may contain no photons of visible light if it is perfectly dark, but the electromagnetic field is still part of the world there. A region may have no electrons passing through it, but the electron field is not locally deleted. Nature does not remove a fundamental field from a patch of space just because no particle is currently being measured there. The field is not a visitor. It is part of the stage, the language, and the possibility of the play itself. And this changes how you think about creation and absence. In everyday life, things seem to begin when an object arrives. A cup appears on a table. A bird enters the sky. A sound breaks the silence. But at the deepest physical level, some beginnings are not arrivals from nowhere. They are changes in the state of something already present. A photon can be emitted when an atom loses energy, not because a tiny ball of light was waiting behind a curtain, but because the electromagnetic field receives energy in a way that becomes a detectable light quantum. An electron and its antiparticle can be created in high-energy processes when conditions allow the relevant fields to be excited in that form. The language sounds strange because the reality is strange, yet it is not fantasy. It is the disciplined result of trying to explain what experiments actually show. The universe behaves less like a warehouse of tiny things and more like an enormous set of fields capable of forming events. This is why empty space can still be physically meaningful even when no particles are present. It has fields in their lowest available condition. It has rules for what can happen if energy is added. It has a hidden vocabulary of possible excitations. But we must be careful here, because this does not mean empty space is secretly full of ordinary particles waiting to jump out. Nor does it mean you can easily extract endless energy from the vacuum. Those are exaggerations. The real idea is subtler and more interesting. The vacuum is not full in the everyday sense. It is not crowded like a room packed with invisible dust. It is full in the sense that the underlying fields remain part of reality, even when their particle-like excitations are absent. That distinction protects the science from becoming a myth. It lets the wonder stay honest. And maybe the most beautiful part is that this view makes matter feel less isolated. You are not built from tiny separate objects floating in a dead background. You are a pattern of excitations in fields that also underlie stars, lamps, stone, air, and the distant light from galaxies. The particles in your body are not separate from the deeper field reality that stretches beyond you. They are local expressions of something more general. You are not spread across the universe as a person, of course, but the fields associated with the particles that compose you are not little personal possessions trapped inside your skin. They belong to the same physical world everywhere. This can feel unsettling at first, because it softens the hard boundary between object and background. The empty space around your hand is not made of your hand, yet the same fundamental kinds of fields that allow your hand to exist are also present beyond it. The world is not a collection of islands floating in nothing. It is more like a continuous underlying order where islands can appear as waves, peaks, and patterns. And when the wave settles, the sea does not disappear. So when you imagine a place where every particle has been removed, do not picture a dead blankness. Picture a quiet field reality with no visible crest, no bright event, no detectable particle standing forward to be named. The silence is real, but it is not the silence of non-existence. It is the silence of instruments before music, of a page before ink, of a sky before lightning. Particles may come and go, appear and vanish, transform and decay, but the fields are the deeper continuity beneath their brief lives. And perhaps that is the lesson hidden here. What disappears is not always the foundation, and what remains unseen may be the very reason anything can appear at all. Why particles can appear as ripples in invisible fields. A particle is not always best imagined as a tiny object hiding inside space, but as a small visible tremor in something you cannot see. That sounds unusual at first, because your senses were built for a world of surfaces. You see stones, drops of rain, sparks, dust, skin, glass, metal. You learn early that things have edges, that they sit in places, that they can be picked up or dropped or pushed aside. So when someone says electron or photon, the mind quietly paints a tiny bead, a little grain of reality moving through the dark. But modern physics asks you to soften that picture. It does not say particles are unreal, and it does not ask you to pretend experiments are illusions. A particle can hit a detector, it can carry energy, it can leave a trace, it can be counted. But the deeper description is that what you call a particle may be a concentrated excitation of a field, a local pulse in something spread everywhere. Think of a guitar string in a dark room. If it is still, you may not notice it, but touch it and a note appears. The note is not a separate little object that was stored inside the string. It is a pattern of motion in the string itself. In a similar spirit, a particle can be understood as a pattern of activity in a field. The field is not a visible material like water or air, and the particle is not simply a wave in the everyday sense, but the image helps your intuition take the first step. What appears as a small thing may actually be a localized behavior of something deeper. This is why physicists often speak of particles as excitations. The word may sound technical, but the meaning is gentle. The field is in a changed state, and that change can show up as a particle. Light gives one of the clearest examples. A photon is the smallest packet of light energy we can detect in many situations. It can arrive at a sensor as one event, one click, one tiny transfer of energy. Yet light also behaves in ways that remind us of waves, spreading, interfering, and bending through openings. The old question was whether light is a wave or a particle. The newer lesson is more subtle. Light is part of a field, and depending on how we interact with it, it can reveal different aspects of its nature. The same kind of shift happens with matter. Electrons can behave like particles when they strike a screen, yet they also create interference patterns under the right conditions, showing that their behavior is not fully captured by the image of a tiny solid speck. This does not mean the electron is just a wave in the familiar ocean sense. It means our ordinary categories are too small. Nature is not required to fit the boxes our daily life created. The reason particles can appear as ripples in invisible fields is that the field is the more complete stage of description. A ripple has a location where it becomes noticeable, but it is also connected to the wider system in which it happens. A small wave on a pond has a crest you can point to, but the crest is not independent of the water. A sound in the air can be heard as a clear note, but the note is not a hard object flying toward your ear. It is a pattern moving through a medium. Quantum fields are not exactly ponds or air, and it would be misleading to push the comparison too far. But the emotional truth of the analogy helps. The world may be made less of little permanent things and more of structured happenings. This is a radical change because it turns particles from miniature building blocks into events with identity. The particle is what the field is doing there, under those conditions. It is a stable enough pattern to be measured, named and studied, but not a tiny classical object with a secret little surface. This is one reason particle physics can sound so strange. In high-energy experiments, particles can be created, transformed, or absorbed. To everyday thinking, this feels like something appearing from nowhere or disappearing into nothing. But in the field picture, it is closer to one pattern changing into another when energy, momentum, and the rules of interaction allow it. The universe is not breaking its own laws. It is speaking in a language deeper than objects. When an atom emits light, a photon appears as the electromagnetic field takes on a new excitation. When particles collide in accelerators, their energy can stir other fields into detectable forms. Scientists do not simply invent these ideas because they are beautiful. They use them because they match what instruments observe with astonishing precision. But what makes the idea so powerful for a listener is not only the accuracy, it is the way it changes the feeling of reality. The solid world around you begins to look less like a collection of hard dots and more like a vast arrangement of patterns, each one held by invisible rules. Your body is not less real because its particles are field excitations. It is more mysterious because its reality depends on layers you cannot see directly. Every atom in your hand carries the quiet signature of this deeper structure. Every bit of light entering your eyes is not just a traveling speck, but a field event meeting the chemistry of vision. Even the warmth you feel from sunlight is an exchange between patterns that began far away and patterns inside your skin. Yet this idea should not be turned into fantasy. It does not mean thoughts are particles rippling through the universe in any magical way. It does not mean everything is imagination. It means physical reality, at small scales, is described by fields whose excitations appear as particles. That is already strange enough. The honest wonder is better than exaggeration, because the real picture is more profound than the myth. A particle is not a tiny marble because nature is not built for human convenience. It is a measurable piece of activity in a field that was there before the measurement, a little crest in a deeper order. And maybe this teaches something beyond physics, quietly, without forcing it. You often judge life by what becomes visible. The action, the result, the object, the words spoken aloud. But beneath every visible thing there may be a wider pattern that made it possible. The particle is the crest, not the whole ocean. The event is the surface, not the whole cause. The world you see is not fake, but it is not final. It is the readable face of something deeper. So when you hear that particles can appear as ripples in invisible fields, do not imagine a ghostly trick or a magical fog. Imagine reality becoming briefly concentrated enough to be noticed. Imagine the hidden grammar of nature forming a syllable. Imagine the universe not as a pile of tiny things, but as a living pattern of fields where what we call matter is the moment the invisible becomes local, countable, and real enough to touch the instruments we build, and eventually, the mind that wonders what touching really means. Vacuum fluctuations, tiny activity beneath stillness. The calmest emptiness in the universe is not perfectly calm. Beneath its silence, physics finds a faint restlessness that never fully goes away. Imagine a bell so quiet that no human ear can hear it. A surface so smooth that no eye can catch a ripple. A dark room so still that even dust seems afraid to move. In everyday life, We would call that peace. We would say nothing is happening. But quantum physics has a different standard for stillness. At the smallest scales, nature does not allow everything to be perfectly fixed, perfectly motionless, and perfectly known at the same time. This is where vacuum fluctuations enter the story. They are not storms inside empty space, not magical sparks bursting from a supernatural void, and not tiny particles casually appearing like fireflies for our entertainment. The real idea is subtler and more powerful. Even when a field is in its lowest possible condition, it is not like a dead, frozen object. It still has unavoidable uncertainty. It still has tiny variations in what can be measured. It still carries a kind of quantum trembling beneath the appearance of quiet. To understand this without drowning in equations, think of trying to hold the surface of a pond absolutely flat, while also knowing every motion it might make. In the ordinary world, you can imagine the pond becoming still. But in the quantum world, perfect stillness would demand too much precision from reality. A field cannot have all of its properties locked down with infinite sharpness. There is always a faint looseness, not because our instruments are bad, but because this looseness belongs to nature itself. Vacuum fluctuations are the name we give to that restless looseness in the vacuum state, the lowest energy condition of a quantum field. This is important because it corrects a common misunderstanding. Many people hear the phrase and imagine empty space as a boiling soup of little particles that constantly appear and disappear. That image can be useful as a rough metaphor in some explanations, but taken literally, it becomes misleading. Physicists do sometimes use the language of temporary particles in calculations, but vacuum fluctuations are not simply ordinary particles popping in and out like miniature ghosts. They are changes and uncertainties in fields, patterns of correlation and activity that can influence real physical situations under the right conditions. In other words, the vacuum is not active in the way a crowded street is active. It is active in the way a sleeping body is active, quiet from the outside, but never absolutely turned off. Your heart does not need to shout for it to be working. A field does not need to produce a visible particle for it to have quantum behavior. This distinction matters because the truth is already strange enough. You do not need to exaggerate it. Even in the absence of detectable particles, the vacuum state is not a simple zero in the human sense. It is the lowest state allowed by quantum rules, and lowest does not mean perfectly empty of motion or possibility. Nature seems to resist the idea of a final, frozen blankness. It allows quiet, but not absolute deadness. It allows a ground state, but not a classical still point where everything is perfectly settled. And this has consequences. Vacuum fluctuations help explain why empty regions are not always physically irrelevant. They are part of the reason the quantum world has a texture different from the clean, mechanical emptiness imagined in older physics. They are tied to the way fields behave near atoms, near boundaries, and inside precise experiments, though each of those effects deserves its own careful explanation. What matters here is the central lesson. The vacuum has a lowest condition, but that condition is not the same as nothing happening. It is a state with built-in uncertainty. That idea may sound abstract, yet it reaches into the way modern science understands reality. Classical thinking says a system at rest can simply stop. Quantum thinking says rest is not the same as total absence of activity. A pendulum in an old physics textbook can hang motionless, but a quantum system cannot always be reduced to such clean stillness. There is always a minimum blur, a minimum uncertainty, a refusal by nature to become a perfectly sharp statue. This is not a flaw in measurement. It is not a temporary gap waiting for better technology. It is part of the structure of the theory that has been tested again and again. And when you apply that lesson to fields, the vacuum becomes something quietly alive with fluctuations, even when no ordinary object is there to be seen. But we should be careful with the word alive. The vacuum is not conscious. It is not thinking. It is not trying to create. It has no desire, no intention, no hidden mind. Its activity is physical, not mystical. The beauty lies in that honesty. The universe does not need to be enchanted to be astonishing. It only needs to be understood deeply enough. A dark region of space can be empty of matter and still not be a dead nothing. A field can be in its lowest state and still not be perfectly still. A measurement can reveal that quiet has structure. This should make you rethink what silence means in nature. Silence in physics is not always the absence of all behavior. Sometimes it is simply behavior too subtle for ordinary senses. A sleeping forest is still exchanging gases. A frozen lake still contains moving molecules. A calm face can hide a racing mind. And at the smallest level, the vacuum hides a kind of uncertainty that cannot be brushed away. This does not mean everything is chaos. In fact, the vacuum is highly ordered in its own way. Its fluctuations are not random noise without rules. They follow the patterns allowed by quantum field theory. They are disciplined restlessness, not meaningless disorder. That is why scientists can describe them, predict their consequences, and use them in serious physics. The vacuum is not a mess. It is a quiet state with depth. And maybe that is the most unsettling part. You are taught to look for reality in what appears. The star, the atom, the flash, the collision, the visible event. But vacuum fluctuations suggest that even when appearances fall silent, reality has not become simple. Beneath the lowest quiet, there is still a softness, a trembling boundary where certainty gives way to probability. And if you sit with that idea long enough, it changes the emotional shape of emptiness. The dark is not necessarily dead. The pause is not necessarily blank. The stillness is not necessarily final. Physics does not tell us that the vacuum is full of fantasy. It tells us something more precise and more haunting. The deepest quiet we know is not perfectly quiet. It is held open by uncertainty. It is touched by fluctuations. It is calm only from a distance. And perhaps that is why the universe could never be understood by the eyes alone. Because the most important movements may be the ones too small to see, too subtle to feel, and too deeply woven into reality to ever truly stop. The energy that remains, even at absolute zero. At the coldest temperature the universe allows, nature still refuses to become perfectly dead. This is the strange lesson hidden inside absolute zero, the temperature we often imagine as the final silence of matter, the point where every atom should stop, every vibration should fade, and reality should become still like a frozen photograph. In everyday thinking, cold means less motion. A warm object has restless atoms moving, shaking, colliding, and carrying energy through their tiny activity. Cool it down and that motion slows. Cool it further and it slows more. So it feels natural to imagine that if you could cool something all the way down to absolute zero, everything inside it would simply stop. But physics does not allow the story to end that cleanly. Absolute zero is not a doorway into perfect stillness. It is the lowest temperature scale can describe, the point where a system has given up as much ordinary heat energy as possible, but not the point where all energy disappears. Even there, matter can still have what physicists call zero-point energy, the minimum energy that remains because quantum systems cannot be forced into a state of perfect rest. This does not mean atoms are secretly warm at absolute zero, and it does not mean there is ordinary heat left to use like fuel. It means the deepest level of cold is not the same as total inactivity. There is a difference between removing thermal energy and removing every possible form of energy. And that difference is where the mystery begins. Think of a child on a swing. In the everyday world, you might imagine bringing the swing perfectly to rest, hanging motionless at the center. But at the quantum scale, objects are not allowed to have every property fixed with perfect sharpness. If an atom were made perfectly still in one exact place, nature would be forced into a kind of impossible precision. Instead, even in the lowest state, there remains a faint, unavoidable spread in motion and position. This is not because the atom is being disturbed from outside. It is not because the experiment is messy. It is built into the rules of the very small. The ground state of a system is not nothingness. It is the lowest allowed way for that system to exist. And lowest does not mean zero in the simple human sense. This is why atoms in a crystal do not become perfectly frozen statues, even as the temperature approaches absolute zero. Their heat vibrations can be reduced enormously, but a tiny quantum motion remains, like a whisper that cannot be silenced without breaking the rules of nature. One of the most beautiful examples is helium. Helium is so light that quantum effects matter strongly. And because of its zero-point motion, it does not freeze into a solid at ordinary pressure, even when cooled extremely close to absolute zero. Most substances would lock into place, but helium remains liquid unless extra pressure is applied. That is not magic. It is a real physical consequence of light atoms refusing, in a quantum sense, to settle down completely. Even at the edge of cold, helium keeps enough restless ground state motion to avoid becoming a normal solid under those conditions. Here the lesson becomes visible. The coldest world is not always the stiffest world. Sometimes the deepest cold reveals behavior that ordinary warmth hides. When scientists cool materials to extremely low temperatures, strange states can appear. Superconductivity, superfluidity, and other collective behaviors where matter acts less like a crowd of separate pieces and more like a coordinated whole. These effects do not happen because the material is energetic in the normal sense. They happen because removing thermal noise allows quieter quantum patterns to emerge. Heat often scrambles delicate behavior. Cooling can reveal it. So absolute zero is not just an endpoint. It is a kind of unveiling. It shows us that temperature is not the same as existence, and heat is not the only kind of energy that matters. A system can be as cold as it can possibly be and still have a lowest energy structure. It can stop behaving thermally without becoming nothing. This is also why reaching absolute zero exactly is believed to be impossible through any finite physical process. You can get closer and closer, reducing heat step by careful step, but the final point retreats like a horizon. The third law of thermodynamics expresses this in a formal way, but the simple meaning is enough. Absolute zero is not a place you casually arrive at. It is a limit nature lets you approach, not a finish line you cross with ordinary cooling. Laboratories have come unimaginably close, cooling atoms to tiny fractions above absolute zero, creating conditions colder than anything found naturally in most of space. Yet even there, the goal is not to create true deadness. The goal is to study matter when almost all ordinary thermal confusion has been removed, when the quiet rules underneath become easier to see. And what those rules show is deeply humbling. Energy is not only the heat you feel in your hand or the flame you see in a fire. Energy can also be the minimum condition required for a physical system to exist at all. It can be locked into the ground state, unavailable as ordinary warmth, not easily extracted, not a hidden battery waiting to be stolen, but still real in the sense that it affects behavior. This distinction matters because zero-point energy is often exaggerated in popular imagination. It is not a simple source of unlimited power. It is not a cosmic trick that lets you break conservation laws. It is the baseline energy of quantum systems. And while it has real consequences, it does not mean we can drain the vacuum or matter like an infinite fuel tank. The honest version is quieter and more profound. Even when you remove heat, something remains, because the universe does not permit perfect nothingness inside a physical system. The final cold is not empty. It has structure. It has a lowest permitted state. It has a kind of restrained restlessness that belongs not to warmth, but to being. And perhaps this changes how you feel about stillness itself. You may think silence means absence, that calm means nothing is happening, that a life, a mind, or a world at rest has become simple. But physics teaches that quiet can be layered. Beneath the obvious motion, there may be a deeper order. Beneath the disappearance of heat, there may be a minimum pulse of existence that cannot be erased. Absolute zero is not a frozen grave for reality. It is the place where reality shows that even its deepest rest is not the same as death. At the bottom of temperature, when almost every ordinary motion has been taken away, nature does not become a blank. It becomes precise, strange, delicate, and quietly alive with the smallest energy it is allowed to keep. Zero-point energy and the restless ground state. A quantum system at its lowest possible energy is not asleep. It is holding the smallest motion reality will allow. This is the idea behind zero-point energy and the restless ground state. And it quietly changes the way you imagine the bottom of nature. In ordinary life, Ground state sounds like the final stop, the lowest floor, the place where everything has settled and nothing more can be taken away. You might imagine a ball resting at the bottom of a bowl, finished with falling, finished with motion, finally still. But in the quantum world, the bottom is not a silent floor. It is more like the lowest note an instrument can play. The note may be low, calm, and stable, but it is still a note. It still has structure. It is not the absence of sound. It is the softest sound permitted by the instrument. In physics, many systems have a lowest allowed state, and that lowest state can still contain energy because the system cannot be squeezed into perfect classical stillness. A tiny object trapped in a region, for example, cannot simply sit there with no motion and no spread at all. If it were perfectly motionless and perfectly pinned down, nature would be forced into a kind of impossible sharpness. Instead, the system has a minimum pattern, a lowest allowed way of existing. This is not heat. It is not hidden fuel. It is not useful energy waiting to be easily harvested. It is the baseline restlessness that comes from being a quantum thing at all. One of the simplest ways to feel the idea is to imagine a string fixed at both ends. It cannot vibrate in just any shape. Only certain patterns fit. The lowest pattern is not no pattern. It is the gentlest pattern that can exist on that string. Quantum systems behave with a similar kind of restriction, though the real mathematics is deeper than the image. They do not accept every possible energy smoothly like a ramp. In many cases, they have allowed levels, and the lowest level is still above the perfectly motionless picture your everyday intuition expects. This matters inside atoms. Electrons do not spiral quietly into the atomic nucleus the way a tiny planet might fall inward if it lost energy. They occupy quantum states, and the lowest stable state still has a spread, a shape, and a minimum energy. If the electron could collapse into a perfect point inside the nucleus, the atom as we know it would not exist. Matter would lose the delicate structure that lets chemistry happen. So zero-point energy is not just an abstract idea hiding in a textbook. It is connected to the stability of the world around you. The table, the air, the water, the molecules in your body all depend on quantum rules that prevent the smallest pieces of matter from behaving like dead classical dust. Molecules carry this lesson even more visibly. The atoms inside a molecule are not connected by tiny rigid sticks. They vibrate around preferred arrangements, and even in the lowest vibrational state, those atoms do not become perfectly still. Their bonds have a minimum quantum motion. Scientists can detect these behaviors through spectroscopy, by studying how molecules absorb and emit light at very specific frequencies. These measurements show that molecular energy comes in steps, and the lowest vibrational step still sits above complete stillness. Even the mass of the atoms matters. Lighter atoms tend to have stronger zero-point motion than heavier ones, which is one reason replacing hydrogen with a heavier form of hydrogen can slightly change reaction rates and molecular behavior. That may sound small, but small does not mean unimportant. In chemistry, biology, and materials science, tiny differences can guide which pathways are easier, which bonds are more stable, and how substances behave under extreme conditions. The restless ground state also reminds us that minimum and nothing are not the same. A valley floor is still part of a landscape. A whisper is still a sound. A resting heartbeat is still a heartbeat. In the same way, the ground state of a quantum system is not the erasure of that system's identity. It is its quietest identity. It carries the least energy available to it, but it still has the shape imposed by the rules around it. Confinement matters. Boundaries matter. Forces matter. The deeper lesson is that energy is not only something added from outside, like fire warming metal or sunlight heating skin. Sometimes energy is built into the very condition of being held in a quantum state. A trapped particle, a vibrating molecule, an atom in its lowest arrangement. Each one teaches the same calm but strange truth. Nature does not always allow the final subtraction you expect. You can remove ordinary excitement. You can reduce disturbance. You can cool, isolate, and quiet a system. But if it remains a quantum system, it may still keep a ground state energy that cannot be peeled away without changing what the system is. This is why zero-point energy is so often misunderstood. It sounds like a door to limitless power, but real physics is more disciplined than that. Ground state energy is not a free treasure chest. Usually, it is not available to do ordinary work, because there is no lower state for the system to fall into. You cannot easily take energy from the floor if there is no basement beneath it. The wonder is not that it gives us infinite fuel. The wonder is that the floor exists above the silence we expected. And perhaps that is what makes the idea so quietly powerful. At the deepest levels, rest is not emptiness. Stability is not death. The smallest systems in nature do not need to be loud to be active. They can be calm and still carry a hidden rhythm, a lowest rhythm, a rhythm so fundamental that without it, atoms would lose their shape, and matter would not behave as the world you know. So when you hear the phrase zero-point energy, do not imagine a magical reservoir glowing behind reality. Imagine instead the universe refusing to make its foundations perfectly numb. Imagine every tiny bound system holding the faintest allowed pulse of existence, not because it is hot, not because it is disturbed, but because to exist quantum mechanically is already to have a shape, and every shape has a cost. The ground state is not a grave. It is the quietest way nature knows how to remain real. The Casimir effect, when empty space pushes metal plates together. Two metal plates with no glue, no charge, no magnet, and no visible hand between them can still feel a tiny pull across what seems like empty space. That is the strange beauty of the Casimir effect. One of those rare ideas in physics where emptiness does not stay philosophical, but becomes mechanical, measurable, almost touchable. Imagine placing two perfectly clean, uncharged metal plates extremely close together, so close that the gap between them is far thinner than a human hair, closer to the scale where ordinary intuition begins to fail. You might expect nothing special to happen. There is no air pressure difference in the usual sense, no hidden spring, no electrical attraction if the plates are truly neutral, no little engine pulling them together. And yet, under the right conditions, a very small force appears, drawing the plates toward each other. It is not strong enough to crush the world or move objects you can easily see, but it is real enough to be measured in careful laboratories, and real enough to matter when machines become extremely tiny. The idea was predicted in 1948 by the Dutch physicist Hendrik Casimir, and at first it sounded almost unreal. Empty space itself, when squeezed between boundaries, can create a force. But to understand it honestly, you have to avoid the easy myth. The Casimir effect is not magic. It is not proof that nothingness is secretly pushing with intention. It does not mean you can place two plates in a room and extract unlimited energy from the vacuum. The truth is more precise and more interesting. In quantum physics, the electromagnetic field has allowed patterns of behavior, and metal plates change which patterns can exist between them. Think of the space between the plates as a very narrow hallway where only certain kinds of waves fit. Long waves may not fit comfortably inside, while outside the plates, more possible field patterns are available. This difference between what is allowed inside the gap and what is allowed outside creates a tiny imbalance. The result is experienced as a force pressing the plates together. It is almost as if the universe is reminding you that boundaries are not passive. When you shape a region of space, you change what the fields are allowed to do there, and that change can have consequences. The plates are not being pushed by ordinary air, because the effect can be studied in vacuum conditions. They are not being pulled by simple static electricity, though real experiments must work very hard to control stray charges, because those could fake or hide the effect. The Casimir force comes from the way conducting surfaces impose restrictions on electromagnetic modes. The word modes may sound technical, but the idea is simple enough. Not every vibration fits in every space. A flute produces certain notes because its length and shape allow certain sound waves. A guitar string has certain tones because its endpoints restrict how it can vibrate. In a very different and much smaller way, two metal plates restrict the allowed electromagnetic field patterns in the gap between them. The vacuum is not filled with ordinary sound, of course, and the plates are not musical instruments in the everyday sense. but the analogy helps you feel the logic. When boundaries decide what patterns fit, the physical behavior changes. The closer the plates are, the stronger this effect becomes, though it is still extremely small by human scale standards. At distances of a few micrometers or less, the force can be detected with sensitive instruments. And when engineers build devices with microscopic moving parts, such tiny attractions can become surprisingly important. In larger machines, the Casimir effect is almost invisible. In micro and nanoscale systems, it can contribute to parts sticking together, a problem sometimes called stiction. This is one of the most fascinating parts of the story. A force born from quantum field behavior in apparent emptiness can become a practical engineering concern. The mystery enters the workshop. The invisible becomes something designers must respect, and the effect is not always as simple as two plates attract. The strength depends on distance, shape, material, temperature, and surface properties. Real plates are not perfectly smooth. Real metals are not ideal. Real experiments must account for contamination, roughness, tiny leftover charges, and the difficulty of measuring incredibly small forces. In special arrangements, with different materials and fluids between surfaces, Casimir-like forces can even be made repulsive, which shows that this is not a crude universal squeeze from nowhere, but a subtle consequence of how fields and boundaries interact. That subtlety is what makes the effect so powerful. It teaches you that empty space is not just an absence where objects sit untouched by the background. It is a physical arena whose allowed possibilities can shift when matter creates borders. Put boundaries in the right arrangement, and the quiet rules beneath the surface become uneven. The force that appears is not dramatic like lightning or gravity pulling planets, but it is profound because it reveals that reality can react to shape itself. A gap is not merely a gap. At very small scales, a gap has rules. A boundary is not merely an edge. It can decide which field patterns are possible nearby. And when possibility changes, force can emerge. That is the part worth sitting with. The Casimir effect takes something that sounds abstract, the behavior of fields in a vacuum, and turns it into a physical nudge between pieces of metal. It is one of the clearest reminders that modern physics does not only describe distant galaxies or violent particle collisions. It also lives in the quiet space between surfaces, in separations too small for your eyes, in the hidden architecture of what can and cannot fit. And maybe that is why the Casimir effect feels so haunting. It shows that even when two things are separated by emptiness, the separation itself is not meaningless. The space between them has a structure, and that structure can act. In life, you may think only the visible things matter, the plate, the hand, the object, the collision. But nature keeps whispering that the unseen conditions between things can shape the outcome just as deeply. The Casimir effect is not empty space behaving like a ghost. It is empty space behaving like physics. Quiet, exact, restrained, and real. Two plates come together not because nothing has become something magical, but because at the smallest scales, nothing between them was never the full story. The gap had rules, the rules had consequences, and the consequences were strong enough to move matter. How empty space can change the energy of atoms. An atom floating in what looks like perfect emptiness is not as alone as it seems, because the space around it can quietly change the energy it is allowed to have. This sounds almost impossible at first, because we usually imagine an atom as a tiny self-contained system, a little world with its own inner rules, carrying electrons in fixed arrangements and absorbing or releasing light only when something directly hits it. But an atom is not sealed away from the universe like a pearl inside glass. It is an open quantum system, surrounded by electromagnetic conditions that affect how its internal energy levels behave. To understand this gently, imagine a singer standing in different rooms. The singer's voice belongs to them, but the room still matters. A narrow hallway, a cathedral, a recording studio, and a padded chamber do not create the voice, yet they change how certain tones echo, strengthen, fade, or return. In a similar but far more subtle way, the environment around an atom changes the electromagnetic possibilities available nearby. Empty space is not a thick material pushing on the atom like wind, and it is not a hidden ocean in the ordinary sense, but it does define what kinds of electromagnetic waves can exist, how they can move, and how the atom can exchange energy with them. This matters because atoms have allowed energy states, like carefully spaced steps, rather than a smooth ramp. When an electron in an atom changes from one allowed state to another, the atom can absorb or emit light of a very specific energy. That is why atoms produce sharp spectral lines, like fingerprints written in light. Hydrogen, sodium, neon, mercury, and other elements each glow or absorb in their own patterns because their internal energy arrangements are different. For a long time, it was tempting to imagine these patterns as belonging only to the atom itself, as if the surrounding vacuum were merely a neutral background. But quantum physics revealed something quieter and stranger. The atom's energy levels are influenced by their interaction with the electromagnetic field. Even when no ordinary light beam is shining on them, the atom and the field are not two completely separate stories. They are coupled. They respond to one another. The atom carries electric charge inside it, and charged particles interact with electromagnetic fields. So even in darkness, even in a carefully prepared vacuum, the atom is still related to the field around it. This does not mean empty space shakes the atom violently or changes it in a way you could see with the naked eye. The shifts are usually extremely tiny, but tiny is not the same as imaginary. A clock can be thrown off by a fraction of a second and still reveal a real effect. A musical note can shift by an amount too small for most ears and still be measurable with the right instrument. Atomic physics is built on this kind of precision. Scientists can measure the frequencies of light absorbed or emitted by atoms with extraordinary accuracy, and those measurements show that the surrounding quantum field cannot be ignored. One of the deepest lessons is that energy levels are not just simple shelves inside the atom. They are corrected, adjusted, and refined by the atom's relationship with its environment. This is why placing atoms near mirrors, inside tiny cavities, or close to surfaces can alter how they behave. A cavity, for example, can restrict or enhance certain electromagnetic patterns, just as the shape of a musical instrument favors certain notes. If an excited atom is placed where fewer matching field patterns are available, it may release light more slowly. If it is placed where the matching patterns are enhanced, it may emit more quickly. This is known in modern physics through ideas connected to cavity quantum electrodynamics, and it shows that empty surroundings can guide the timing and probability of atomic transitions. The atom has not changed into a different element. Its nucleus has not been replaced. Its identity remains, but the space around it has changed the menu of possibilities. That is a profound idea. The behavior of something as tiny and precise as an atom can depend on the architecture of the emptiness around it. In ordinary life, we often treat emptiness as irrelevant. If nothing is touching an object, we assume nothing is influencing it. But at the quantum level, influence does not always look like contact. The conditions around a system help decide what kinds of interactions are possible. A mirror is not merely a reflective surface when viewed this way. It changes the electromagnetic environment nearby. A small cavity is not merely a hollow container. It reshapes the field patterns inside it. Even distance from a material surface can matter, because atoms and surfaces can interact through subtle electromagnetic effects that become noticeable at very small scales. This is not fantasy, and it is not a violation of conservation of energy. It is the disciplined reality of systems that do not exist in isolation. The atom's energy is calculated not only by looking at the atom as a lonely object, but by including how it couples to the fields around it. That is why empty space can change the energy of atoms, not by becoming a mysterious substance, but by being part of the physical conditions that define the atom's possible states. And this is why precision spectroscopy became one of the great windows into invisible physics. By studying tiny shifts in atomic light, scientists can learn about effects far too small to see directly. The atom becomes a kind of microphone for the vacuum, not because it hears sound, but because its energy levels respond to the field conditions around it. Every spectral line is more than a color. It is a report from the hidden structure of reality. When the line appears slightly shifted, it is telling us that the atom is not living in a perfectly neutral emptiness. It is living inside a field environment with rules, boundaries, and subtle activity. The beauty of this idea is that it turns atoms into sensitive witnesses. They reveal what the human senses cannot. They show that what surrounds a thing can help shape what the thing is allowed to do. And maybe this is the larger lesson. Quiet but unforgettable. Nothing in the universe is completely isolated. Even the smaller systems carry relationships. Even the emptiest surroundings have conditions. Even a single atom held in darkness speaks to the space around it. So when you picture empty space changing the energy of atoms, do not imagine a dramatic force crashing into matter. Imagine something far more delicate, a quiet adjustment in the allowed music of the atom, a barely perceptible tuning of its inner notes by the invisible room it inhabits. The atom remains small, but the lesson becomes vast. Reality is not built only from objects. It is also built from the conditions around objects, the silent arrangements that decide which possibilities can sing, which remain quiet, and how even emptiness can leave a measurable mark on the heart of matter. The Lamb shift and the vacuum's tiny fingerprint. A tiny difference in hydrogen once forced physicists to admit that empty space leaves fingerprints on matter. It was not a dramatic explosion, not a new planet in the sky, not a machine tearing open the universe, but a small mismatch in the color and energy of one of the simplest atoms in existence. Hydrogen should have been easy, almost humble. One proton, one electron, the cleanest natural laboratory you could ask for. And yet, hidden inside this simplicity was a clue so precise that it changed modern physics. According to an earlier theory that had already explained a great deal, two particular energy states in hydrogen were expected to be the same. They looked equal on paper. They should have lined up perfectly. But in 1947, Willis Lamb and Robert Rutherford measured hydrogen carefully using microwave techniques and found that these two states were not exactly equal after all. One sat just a little higher than expected. The difference was tiny, almost absurdly small by everyday standards, but it was real. And because it was real, physics had to listen. This is what became known as the Lamb shift. A small shift in the energy levels of hydrogen caused by subtle quantum effects that earlier models had not fully included. To a casual eye, this may sound like a technical detail, something only a specialist would care about, but the meaning is much larger. The Lamb shift showed that an atom is not simply a little electron moving around a proton in a clean private system. It is also affected by the quantum fields around it, including the electromagnetic field that remains active even when no ordinary light is being shone on the atom. The electron is charged, so it interacts with electromagnetic fields. And in quantum electrodynamics, the theory that explains light and charge particles together, that interaction is not optional. Even in the ground-level quiet of the vacuum, the electron is influenced by its own field and by subtle field effects surrounding it. One way to picture this, gently and imperfectly, is to imagine an electron not as a perfectly sharp speck, but as something whose position and behavior are slightly blurred by quantum uncertainty. Near the proton, the electric attraction is extremely strong. Some electron states spend more time closer to the nucleus than others, so they feel this influence differently. The vacuum's tiny disturbances and the electron's interaction with its own electromagnetic field slightly adjust the atom's energy, almost like a musician discovering that the room changes one note more than another. But this is not ordinary echo, and it is not mystical vibration. It is a measured correction in one of nature's simplest systems. The Lamb shift became one of the great triumphs of quantum electrodynamics because the theory could calculate the shift with extraordinary accuracy. In fact, the need to explain this tiny difference helped drive the development of the mathematical tools that made quantum electrodynamics one of the most precisely tested theories in science. That is the astonishing part. A tiny imperfection in hydrogen became a doorway into a deeper description of reality. The universe did not reveal itself through loudness, but through precision. A difference too small for human senses became a message from the vacuum itself. And the message was clear. The emptiness around an atom is not irrelevant. It participates, not as a visible substance, not as a hidden wind, but as the field environment in which charged particles exist. Another piece of the story is called vacuum polarization. Because of quantum effects, the region around a charge can behave as if the vacuum slightly rearranges the way the charge is experienced at very small distances. Again, this does not mean empty space is filled with ordinary little objects swarming like insects. That image is too crude. It means the fields and interactions around charged particles modify what the atom effectively feels. The proton's electric influence is not simply a naked, untouched thing at every scale. Quantum effects refine it. The electron's own field contributes too. Together, these corrections shift the allowed energy levels just enough to be detected. And when scientists detect that shift, they are not seeing the vacuum directly like a photograph. They are seeing its consequence inside the atom's behavior. This is why the Lamb shift can be called the vacuum's tiny fingerprint. A fingerprint does not need to be large to prove contact. It only needs to be distinctive. The Lamb shift is distinctive because without these quantum field corrections, the measured hydrogen spectrum would not match reality. The atom becomes a witness. Its light becomes testimony. Its tiny energy difference says, the deeper world is not exactly the simple world you first imagined. And perhaps this is what makes the story so powerful for anyone listening quietly. We often think truth arrives as a giant revelation, something obvious enough to shake us immediately. But science often advances through small, stubborn details that refuse to disappear. A tiny disagreement between theory and measurement can be more important than 1,000 beautiful assumptions. Hydrogen, the simplest atom, did not obey the old picture perfectly, and because it did not, physicists had to build a more accurate one. That is how knowledge grows. Not by forcing nature to fit our ideas, but by letting nature embarrass our ideas gently until they become deeper. The Lamb shift teaches that the invisible is not unreal, that small effects can carry enormous meaning, and that the quietest measurements can expose the hidden architecture of matter. It also teaches humility. If one electron in one hydrogen atom can carry evidence of quantum fields, then the world around you is filled with layers your senses were never designed to notice. The light from a lamp, the atoms in your skin, the air you breathe, the chemistry that keeps you alive, all of it rests on rules so delicate that a tiny shift in hydrogen helped reveal them. So when you hear about the Lamb shift, do not think of it as a dry technical correction. Think of it as a whisper that changed physics. Think of an atom so simple that it seemed fully understood until a small difference opened a hidden door. Think of empty space placing the faintest signature on matter, not with drama, not with magic, but with a precision so deep that once you measure it, the universe can never look blank again. Virtual particles, what they mean and what they don't mean. A virtual particle is one of the most misunderstood ideas in physics, because the name makes it sound like a tiny ghost, briefly sneaking into reality before disappearing again. That image is tempting, and it has appeared in countless popular explanations, but it is also the place where confusion begins. Virtual particles are not little ordinary particles that you could catch if your detector were fast enough. They are not miniature sparks borrowing energy from the universe like thieves on a timer. They are not proof that things can appear from nothing in the simple, magical way the imagination wants. In modern quantum physics, virtual particles are best understood as parts of a calculation. Internal features in the mathematical diagrams physicists use to describe how real particles interact. When two electrons repel each other, for example, the interaction can be described using the language of a virtual photon. But this does not mean a tiny visible photon flies between them like a bullet passing a message. It means the electromagnetic field interaction can be represented in a useful way, and the virtual photon is part of that representation. It helps physicists calculate how the interaction behaves. It carries energy and momentum in the bookkeeping of the theory, but it does not satisfy the same conditions as a real photon that can travel freely, hit a detector, and be counted as light. A real photon can leave the sun, cross space, enter your eye, and trigger vision. A virtual photon is not that kind of thing. It is not directly observed. It appears inside the machinery of a theory that predicts what real experiments will measure. This distinction may sound small, but it protects the truth from becoming a myth. Physics often uses models, diagrams, and language that help us work with reality without always being literal pictures of what is happening. A map can show a border as a line, but the border is not literally a glowing line drawn across the ground. A weather forecast can use arrows to show wind, but the arrows are not flying through the air. Feynman diagrams, the famous drawings used in particle physics, are similar in spirit. They look like little stories of particles meeting, exchanging, transforming, and leaving, but they are not simple cartoons of microscopic events. They are tools for organizing calculations about probabilities. The lines that enter and leave the diagram can often represent real particles that are prepared or detected. The internal lines, the ones hidden inside the interaction, are what people call virtual particles. They are part of the mathematical path from question to prediction. And because the predictions work so extraordinarily well, virtual particles are not meaningless. But not meaningless is different from ordinary objects flickering in and out of existence. This is where the careful beauty lives. Virtual particles are real in the way a powerful theoretical ingredient can be real. They help describe measurable effects. They are embedded in equations that match experiments, and they reflect the fact that fields interact in ways our everyday object-based imagination cannot easily picture. But they are not real in the same way as an electron detected in a cloud chamber or a photon absorbed by a sensor. If you try to think of them as tiny things that physically pop into the world for a moment, you will quickly be led into false ideas. One common myth says they borrow energy from emptiness, live briefly, and then pay it back before the universe notices. This phrase is memorable, but it is not a good literal explanation. The uncertainty principles in quantum physics do not give nature permission to break conservation laws like a loophole in a contract. Conservation still matters. What changes is that inside a quantum calculation, intermediate states do not have to behave like freely traveling particles you can isolate and observe. They are part of the structure of interaction, not little temporary violations running loose in space. So when you hear that forces are carried by virtual particles, hold the phrase gently. It is useful, but it is not the full picture. The deeper picture is that fields influence one another, and virtual particles are a way of describing that influence in a specific mathematical approach. In some situations, especially when interactions are weak enough to be treated step by step, this language works beautifully. In other situations, the field behavior may be better described without imagining individual virtual particles at all. This means virtual particles are not the secret furniture of the vacuum, scattered everywhere like invisible dust. They are not a hidden population waiting just behind perception. They are more like the grammar marks inside the language of quantum field theory, helping physicists describe how real outcomes emerge from field interactions. And yet, the idea remains fascinating because it shows how far reality is from the simple pictures we inherit. You want the world to be made of clear objects pushing and pulling one another across empty gaps. Quantum theory gives you something more subtle. Interactions that can be calculated as if unseen messengers pass between particles. Even though the messengers are not ordinary detectable travelers, it is as if nature lets us use a story that works, while quietly warning us not to mistake the story for a photograph. This is not a weakness of science. It is one of its strengths. Science does not always hand you a comforting image. Sometimes it hands you a tool that predicts with breathtaking accuracy and then asks you to be humble about what the tool means. Virtual particles live in that space between visualization and reality. They remind you that understanding is not always the same as picturing. There are truths too small, too abstract, or too deeply structured to fit inside the mind's usual images. And perhaps this is why the phrase virtual particle feels so strangely alive. It points to something that matters, but not in the simple way the word particle suggests. It belongs to the invisible accounting of interactions, to the hidden scaffolding behind forces, to the way fields exchange influence without needing to become little marbles in the dark. So the honest lesson is this: virtual particles are not fake, but they are not ordinary particles either. They are not fantasy, but they are not tiny ghosts. They are not directly seen, but the theories that use them can describe the world with astonishing precision. They are a reminder that the universe is not obligated to be imaginable before it is true. And when you let go of the cartoon, the real wonder becomes deeper, because you are no longer picturing emptiness filled with magical sparks. You are glimpsing something stranger and more disciplined, a reality where interaction itself has hidden structure, where forces can be calculated through invisible internal possibilities, and where the smallest events are not always things moving through space, but relationships unfolding in a language more precise than the pictures in your head. Why boiling space is a metaphor, not magic. When people say empty space is boiling, they are not describing a cosmic liquid bubbling in the dark, but reaching for a metaphor because ordinary language has run out of clean handles. The phrase is powerful, almost too powerful, because it makes the vacuum sound like a cauldron beneath reality, a hidden ocean frothing with particles that appear and vanish before your eyes could ever catch them. It is easy to imagine space as something alive in a dramatic way, bursting, foaming, spawning tiny sparks from nowhere. But real physics is both quieter and more precise than that. The quantum vacuum is not a magical soup. It is not a supernatural engine. It is not a place where the universe breaks its own rules for a fraction of a second and hopes no one notices. Boiling space is a picture, not a literal event. And if you hold the picture too tightly, it begins to teach the wrong lesson. Boiling, in everyday life, means a liquid is heated until bubbles form and rise. Pockets of vapor growing because molecules have gained enough energy to change state. Empty space is not a liquid sitting on a cosmic stove. It has no surface where bubbles pop, no temperature in the ordinary boiling water sense, no little droplets of reality splashing into existence. What physicists are usually trying to communicate with a metaphor is that the vacuum is not a simple dead blank. Its fields do not behave like perfectly flat, motionless nothingness. They have quantum uncertainty. They have measurable consequences. They allow interactions to be described in ways that look restless from the viewpoint of classical intuition. But restlessness is not the same as chaos, and metaphor is not the same as mechanism. The danger comes when a poetic phrase becomes a fake explanation. Someone hears that space is boiling and thinks particles are literally appearing from nothing, fully real for a moment, then disappearing like bubbles in water. That image can feel exciting, but it is not the careful truth. In quantum field theory, what we call vacuum activity is described through fields, probabilities, correlations, and interactions. Sometimes calculations use the language of virtual particles, but those are not ordinary particles flying around in secret. They are part of the way the theory organizes possible interactions. Sometimes people say energy is borrowed for a moment, but that phrase is also a shortcut and a risky one. The universe is not a bank with particles taking tiny loans and paying them back before being caught. Conservation laws are not being casually violated like rules in a game. The mathematics is more disciplined than the cartoon. The vacuum's behavior comes from the structure of quantum fields and the limits on what can be sharply defined, not from a loophole that allows magic. And yet, the metaphor survives because something real does need to be expressed. If you compare the vacuum to the perfectly empty space imagined in older, simpler pictures, then yes, it is strange. It is not blank like an untouched sheet of paper. It is more like a page that already has grammar before any sentence is written. It does not contain ordinary visible matter everywhere, but it still has the rules and field structure from which physical events can arise. This is why the metaphor of boiling can be useful for a moment. It shakes the listener out of the idea that vacuum means total nothingness. But after it does that job, you must set it down carefully. Otherwise, it becomes misleading. Good science communication often begins with a metaphor, but it cannot end there. A metaphor is a bridge, not a home. You cross it to reach a better understanding. But if you start living on the bridge, you mistake the bridge for the landscape. The real vacuum is not best imagined as a frantic foam, but as the lowest state of fields that can still have subtle structure. It is quiet, but not simplistic. It is empty of ordinary particles in certain conditions, but not empty of physical meaning. And some of its effects are not merely philosophical. They show up in real measurements, in tiny shifts in atomic energy, in forces between surfaces at extremely small distances, in the precision language of particle interactions. These effects are not caused by literal bubbles bursting in space. They are caused by the way fields and boundaries and quantum rules shape what can happen. That distinction may sound less cinematic, but it is more awe-inspiring, because it shows that the universe does not need fantasy to be deep. It only needs honesty. The vacuum can be strange without being magical. It can be active without being alive. It can influence matter without having intentions. It can resist our simple pictures without becoming a myth. This matters because modern physics is already difficult enough. An exaggeration makes it feel easier at first, while making real understanding harder later. If you tell someone space is boiling and leave it there, they may walk away with a vivid image but a false belief. If you tell them the metaphor points toward quantum uncertainty in fields, toward the fact that the lowest state of reality is not the same as a classical zero, then the image becomes a doorway instead of a trap. The listener learns not only that the vacuum is strange, but how to think carefully about strangeness. That is the deeper lesson. Not every powerful sentence is literally true. Not every beautiful image should be trusted all the way down. Physics often asks you to hold two things at once: wonder and discipline. Wonder lets you approach the impossible-looking idea. Discipline keeps you from turning it into a fairy tale. Boiling space belongs exactly there, between wonder and discipline. It is a dramatic way of saying the vacuum is not perfectly featureless, but it should not be treated as a photograph of what is physically happening. The truth is more subtle. Fields remain even in their quietest condition. Their behavior cannot be reduced to ordinary stillness. Their effects can sometimes be measured, and our best descriptions often use abstract tools that do not translate neatly into everyday images. So the next time you hear that empty space boils, do not picture a cosmic pot filled with magical bubbles. Picture instead the failure of ordinary emptiness as an idea. Picture the human mind trying to describe a level of reality where stillness has structure, where absence has rules, where the quiet beneath matter is not dead, but deeply ordered. The metaphor is not the miracle. The real miracle is that when the metaphor is stripped away, the vacuum remains strange enough on its own. The quantum vacuum around every atom. Around every atom, there is an invisible neighborhood that your eyes will never see. But without it, matter would not behave the way it does. We usually picture an atom as a tiny center with electrons somehow moving around it, like a small private system floating in empty space. But this picture is too lonely. An atom is not sealed inside a silent bubble. It lives inside the quantum vacuum, and the vacuum around it is not just the leftover emptiness between one piece of matter and another. It is the field environment in which the atom's charged parts exist, respond, and interact. This does not mean every atom is surrounded by a glowing mist, or that tiny particles are swarming around it like insects. The truth is quieter. The atom is immersed in electromagnetic field conditions that remain present even when there is no ordinary light shining on it. Because electrons and protons carry electric charge, they are never completely unrelated to those fields. Their behavior is partly defined by the way charge and field belong to the same physical story. Think of an atom not as a bead placed in a blank room, but as a small island whose shoreline is constantly shaped by the invisible sea around it. The island is real, but so is the waterline. The atom has its own structure, but the field around it helps decide how that structure expresses itself. One of the most important examples is spontaneous emission. An excited atom can release light and drop to a lower energy state, even when no outside light beam comes along to force it. In older thinking, this can feel strange, as if the atom simply chooses a random moment to give up energy. But in quantum physics, the surrounding vacuum field plays a role. The atom is coupled to the electromagnetic field, and because the field has quantum properties even in its lowest state, the excited atom is not isolated from the conditions that allow light to be emitted. The vacuum does not command the atom like a conscious force, and it does not push it with an ordinary hand, but it provides the physical field into which the atom can release a photon. In this sense, the darkness around the atom is not just darkness, it is the open possibility of radiation. This is why atoms do not behave as if they are floating in a meaningless void. Their transitions, lifetimes, and interactions can depend on the field environment around them. Place an atom near a surface or inside a carefully designed optical cavity, and its behavior can change because the allowed electromagnetic surroundings have changed. The atom is the same element, but its invisible neighborhood is different. This is not science fiction. It is studied in laboratories where atoms, mirrors, and light fields are controlled with extraordinary care. The lesson is subtle but powerful. Empty space near matter is not a passive absence. It has conditions that can influence how matter exchanges energy. Around every atom, there is also a constant relationship between charge and the field it creates. An electron does not simply sit in an atom like a pebble in a bowl. It is described by a quantum state, spread in a way that gives the atom its size, shape, and chemical behavior. The electric field of the nucleus, the electron's own presence, and the surrounding quantum fields all belong to the same deeper framework. This is part of why atoms can have stable shapes without collapsing into featureless points. The atom is not held together by tiny mechanical hooks. It is held by quantum rules, electromagnetic attraction, allowed states, and the limits nature places on how sharply things can be confined. The vacuum around the atom is not the main actor in every part of that story, but it is never completely irrelevant. It is the field background in which the story can happen. Even the way atoms attract one another at short distances can be understood through fluctuating electric behavior. Neutral atoms have no overall charge, but their internal charge distribution can momentarily become uneven. These tiny fluctuations can induce related fluctuations in nearby atoms, leading to weak attractions known as van der Waals forces. These forces help geckos cling to walls, influence how molecules stick together, and shape the behavior of liquids and solids. That is remarkable when you pause with it. Matter can feel a pull not only because of obvious charges or chemical bonds, but because even neutral atoms are never perfectly dead, rigid objects. Their inner charge patterns can shift, and the electromagnetic field helps carry the relationship between them. In more refined situations, near surfaces or at larger separations, related effects are described with ideas such as Casimir polar forces, where the quantum vacuum and material boundaries help shape the attraction between atoms and surfaces. Again, this is not magic. It is not emptiness turning into glue. It is the consequence of fields, charges, and allowed fluctuations interacting under real physical rules. The deeper you look, the more the atom becomes less like a tiny solar system and more like a delicate agreement between matter and field. The vacuum around it is not a decoration. It is part of the context that gives atomic reality its full behavior. And this should change the way you imagine your own body. Every atom in your skin, your blood, your eyes, your bones, exists in this invisible field environment. You do not feel it directly. You do not wake up sensing the quantum vacuum around carbon, oxygen, hydrogen, and nitrogen atoms inside you. But the stability of matter, the emission and absorption of light, the weak attractions between molecules, the chemistry of life, and the properties of materials all depend on rules that operate far beneath ordinary perception. The world feels solid because these hidden relationships are reliable. It feels calm because the underlying field behavior is orderly enough to build atoms, molecules, cells, and thought. That is the quiet wonder here. The vacuum around every atom is not an empty halo. It is not a mystical aura. It is the invisible physical context in which charged matter participates in the universe. When you touch a table, see a color, breathe air, or feel warmth, you are experiencing the large-scale result of countless atomic systems interacting with fields. The atom is small, but it is not alone. The vacuum is quiet, but it is not meaningless. And perhaps the most beautiful part is that reality does not need to be loud to be intimate. Around every atom, even in the deepest apparent stillness, there is a hidden relationship between what exists and the field conditions that allow it to exist. The universe is not made of isolated specks scattered through emptiness. It is made of systems within systems, every atom surrounded by an invisible order, every piece of matter carrying the trace of a deeper field world, every solid thing quietly reminding you that nothing in nature truly stands apart from the space around it. How empty space shapes light. Light does not simply pass through empty space. In a quiet but exact way, empty space tells light how to move. At first, this feels wrong, because we are used to thinking of light as the thing that reveals space, not something shaped by it. You switch on a lamp and the room appears. You look at the stars, and their light seems to fly across a dark nothing, untouched until it reaches your eyes. But physics sees a deeper relationship. Light is not a little object thrown through a meaningless void. It is an electromagnetic disturbance, and even in empty space, that disturbance follows rules. The vacuum does not slow light the way glass or water does, and it does not scatter light like fog. In the simplest, cleanest conditions, light moves through vacuum at the fastest speed nature allows. And that speed is not random. It is built into the structure of electromagnetic reality itself. This is the first way empty space shapes light. It gives light its natural pace. When light travels through glass, it appears to slow because it interacts with the material's charged particles, being absorbed and re-emitted in a complicated collective way. But when light travels through true vacuum, there is no glass, no air, no dust required. Still, light does not move infinitely fast. It has a limit. That limit is one of the deepest facts in physics. Not just a speed for light, but a speed limit for cause and effect. A signal, a change, a piece of information, a disturbance in a field cannot outrun it. So the darkness between stars is not an empty road with no rules. It is a physical condition where light's motion is disciplined by the architecture of nature. And this single fact changes how you understand the universe. Because light has a finite speed, looking outward means looking backward. The moon is seen slightly as it was, the sun as it was minutes ago, nearby stars as they were years ago, distant galaxies as they were millions or billions of years ago. Empty space does not merely separate objects, it turns distance into time. It makes the sky into a memory field. Every beam of light is a delayed message, and every telescope is a machine for receiving the past. This is not because space is doing something dramatic to light in the way a prism bends color, but because light needs time to cross emptiness. The gap itself becomes part of the story. And the larger the gap, the older the message. Yet empty space shapes light in another way too, not by touching it like a material, but by giving it geometry to follow. In Einstein's picture, gravity is not simply a force pulling light the way a rope pulls a stone. Massive objects curve space-time, and light follows the straightest possible path through that curved geometry. To us, that path can look bent. This is why light from a distant galaxy can be curved around a massive cluster of galaxies, creating arcs, rings, or multiple images in the sky. The light is still moving locally as light should, but the emptiness it crosses is not a flat, featureless backdrop. Its geometry has been shaped by mass and energy, so a beam of light can arrive at your telescope from a direction that is not the simple straight line your intuition expects. Empty space, when curved, becomes a lens. Not a glass lens you can hold in your hand, but a gravitational lens made from geometry itself. This is one of the most beautiful ideas in modern science. The universe can magnify its own distant objects because space has shape. The darkness between galaxies can quietly bend the paths of ancient light and reveal things that would otherwise remain hidden. And then there is expansion. On the largest scales, empty space is not merely a static distance between galaxies. The universe itself is expanding. And as light travels through that expanding space, its wavelength can be stretched. This is called cosmological redshift. It is not exactly the same as light getting tired, and it is not because the light is rubbing against space like a wheel on a road. Rather, As the fabric of cosmic distance grows while the light is traveling, the light's wavelength grows with it. By the time it reaches us, it may be redder, cooler, and less energetic than when it began. In extreme cases, light that started as visible or ultraviolet may arrive as infrared or radio waves. This means empty space does not only carry light. Across billions of years, the expansion of space can change the light's identity as we receive it. A photon leaving an early galaxy begins its journey with one character and arrives with another, stretched by the history of the cosmos itself. In that sense, light is a traveler that cannot cross the universe without collecting the universe's story into its wavelength. Even the color of distant galaxies becomes a record of space expanding while the message was on its way. And in the most extreme environments, physics suggests another subtle possibility. The vacuum itself can behave differently when enormous electric or magnetic fields are present. Around neutron stars, especially magnetars, magnetic fields can be so powerful that the quantum vacuum is predicted to respond in a way that slightly affects how light of different polarizations moves. This effect is often called vacuum birefringence. It is not something you would ever notice in ordinary empty space around Earth. And it is not the vacuum becoming glass in the everyday sense. It is far more delicate. A prediction that under extreme conditions, the quantum properties of the vacuum can make it act a little like a medium for light's polarization. Scientists study such effects because they offer clues about how light and quantum fields behave under conditions impossible to recreate easily in ordinary life. This is where the idea becomes humbling. The vacuum is usually the closest thing we have to perfect transparency, yet under the right cosmic extremes, even transparency may carry a signature. Empty space is not always the same everywhere when fields, gravity, expansion, and boundaries enter the picture. It can be flat or curved, quiet or stretched, nearly featureless or subtly responsive. And light, which seems so pure, becomes the witness to all of it. It tells us whether space has expanded. It tells us whether gravity has bent its path. It tells us how far away a galaxy is, how fast the universe has grown, and what invisible structures lie between the source and the observer. You might think of light as the universe's messenger, but a messenger is shaped by the road it travels. A letter carried through rain arrives stained. A voice echoing through a canyon arrives changed. A beam of light crossing the cosmos arrives carrying the imprint of space itself. This does not make light unreliable. It makes it informative. Every change becomes a clue. Every delay, bend, stretch, and polarization shift becomes a way of reading the hidden conditions between here and there. And perhaps that is the quiet wonder of this topic. Empty space shapes light not by blocking it, but by giving it a world to cross. The path matters, the distance matters, the geometry matters, the expansion matters. Even the most transparent emptiness is not a meaningless absence, because light cannot travel without obeying what that emptiness allows. So the next time you see sunlight on a wall, starlight in the night sky, or the faint glow of a galaxy in an image from a telescope, remember that you are not seeing light alone. You are seeing light after space has spoken to it. You are seeing a message shaped by distance, curved by gravity, stretched by cosmic history, and delivered to your eyes as evidence that even emptiness has a quiet hand in how reality becomes visible. Why the vacuum can have pressure. Pressure sounds like something that needs matter, like air pressing against your skin or water squeezing a diver in the deep. So the idea that a vacuum can have pressure feels almost like a contradiction waiting to collapse. How can emptiness push? How can the absence of ordinary particles have anything like weight, tension, or force? The trick is that physics uses the word pressure more deeply than everyday life does. In daily experience, pressure usually comes from particles hitting surfaces. Air pressure happens because countless gas molecules move and collide with walls, your body, and each other. Water pressure happens because the water above pushes on what lies below. In that familiar picture, no particles should mean no pressure. But the vacuum of modern physics is not just air removed from a box. It can be described as a physical state with energy, fields, and a relationship to space itself. And once energy becomes part of the story, pressure can appear in a broader sense, not as little particles bouncing around, but as a property of how a system responds when space changes. Imagine stretching a rubber sheet. The sheet may not be filled with gas, but it still has tension. It resists being changed. It carries stress. In physics, pressure and tension are related ideas. Pressure pushes outward, tension pulls inward, and both describe how energy is distributed and how a system reacts to being compressed or expanded. So when physicists say the vacuum can have pressure, they are not imagining tiny invisible air molecules hiding in emptiness. They are saying that the vacuum state can have a stress-like property, a way of contributing to the behavior of space and matter, even without ordinary material inside it. This becomes especially important in Einstein's theory of gravity, where gravity does not respond only to mass in the simple old sense. It responds to energy, momentum, pressure, and stress. A hot gas, a beam of radiation, a magnetic field, and even a vacuum energy term can all contribute to the gravitational story, because they are part of the total physical content of the universe. This is one of the places where intuition breaks. You may think gravity only cares about heavy things, but the deeper theory says it cares about the full pattern of energy and pressure. Pressure is not just a local inconvenience in a tire or a bottle. It is one of the ingredients that can shape space-time. Now, the vacuum's pressure is especially strange because, in the simplest cosmological picture, vacuum energy is associated with negative pressure. Negative pressure does not mean less than nothing in a magical sense. It means the vacuum behaves more like tension than ordinary gas pressure. A normal gas in a box resists compression because its particles hit the walls more strongly when squeezed. If the box expands, the gas thins out and its energy density drops. Vacuum energy, in the idealized picture, behaves differently. Its energy density can stay the same as space expands. That is deeply unusual. If you make more space and the same energy density fills that new space, the accounting of energy and expansion becomes unlike anything familiar from ordinary matter. The negative pressure is the way physics expresses this unusual behavior. It is not a hand pushing from outside the universe. It is not emptiness deciding to stretch space. It is a property written into how that vacuum-like energy relates to expansion. And in general relativity, strong enough negative pressure can have repulsive gravitational effects on cosmic scales. This is why the pressure of the vacuum is not just a technical curiosity. It sits close to one of the biggest mysteries in cosmology: why the expansion of the universe is accelerating. Scientists often connect that acceleration with something called dark energy, and the simplest model of dark energy acts very much like vacuum energy with negative pressure. But honesty matters here. We do not fully know what dark energy is. We do not know whether it is truly constant vacuum energy, something dynamic, or a sign that our understanding of gravity needs refinement at cosmic scales. What we do know is that the universe's expansion behaves as if a component with negative pressure is dominating its large-scale evolution. That is already astonishing enough. It means pressure, a word you may associate with balloons and oceans, becomes part of the fate of galaxies. Yet there is another side to this idea, more local and more concrete. In quantum field theory, vacuum states can also produce measurable stresses when boundaries or conditions restrict fields. This is why the pressure-like language is useful in effects where surfaces feel tiny forces, because the allowed field patterns differ from place to place. The vacuum's pressure is not always one simple universal push. It depends on context, on fields, geometry, and the physical situation being described. This is why we must be careful not to turn the idea into a slogan. The vacuum does not have pressure the way air in your lungs has pressure. It does not blow like wind. It does not shove your hand. You cannot open a jar of vacuum pressure and pour it out. Its pressure is a deeper property of field states and space-time physics, visible only in precise experiments or in the largest behavior of the cosmos. And maybe that is what makes it so haunting. The universe keeps teaching us that familiar words survive only by changing meaning. Empty does not mean simple. Pressure does not always mean particles. Stillness does not always mean zero. A vacuum can have pressure because vacuum in physics is not a dead absence, but a state with structure, energy, and gravitational meaning. It can resist, contribute, curve, stretch, or influence depending on the conditions. And when you let that thought settle, the darkness between stars no longer feels like a passive gap. It becomes part of the architecture, not alive, not conscious, not magical, but physically meaningful. The vacuum can have pressure because reality is not made only of things that bump into other things. It is also made of states, fields, stresses, and quiet relationships that decide how space behaves when almost everything visible has been taken away. So the next time you hear the word emptiness, do not imagine weakness. In physics, even emptiness can have a kind of tension, a silent pressure written not in air or water, but in the deepest bookkeeping of the universe itself, vacuum energy and the cosmological constant problem. The universe may be expanding because of something so small, so quiet, and so badly understood that it has become one of the deepest embarrassments in modern physics. It begins with a simple idea that does not feel dangerous at first. Empty space might have energy of its own, not energy in the ordinary sense of a flame, a battery, a moving object, or a warm piece of metal, but a background energy associated with the vacuum itself, a kind of baseline contribution written into the fabric of physical theory. In Einstein's theory of gravity, this possibility can appear as what is called the cosmological constant, a term that acts as if space itself carries a fixed energy density. Einstein originally introduced this term for a very different reason, trying to make a static universe possible before the expansion of the universe was discovered. Later, when galaxies were found to be moving away from one another, the static universe was abandoned, and the cosmological constant seemed like a historical leftover. But the universe has a way of returning old questions in new disguises. Near the end of the 20th century, observations of distant exploding stars showed that cosmic expansion is not merely continuing, but accelerating. Something seems to be driving space to expand faster over time on the largest scales. The simplest explanation is that a small positive cosmological constant exists, or something very much like it. In that picture, empty space itself contributes a gentle but persistent effect that becomes important only when the universe grows large and matter becomes spread thin. This is already strange, but it is not yet the real problem. The real problem appears when physicists try to connect this cosmic effect with the vacuum energy predicted by quantum field theory. In quantum physics, fields have lowest energy states, and those states can contribute to what we call vacuum energy. If you add up those contributions in a straightforward way, even with reasonable cutoffs and careful thinking, the natural expectation can become absurdly larger than the tiny value cosmology seems to allow. Not just a little wrong. Not a factor of 10. Not a missed decimal. The mismatch is often described as one of the worst disagreements between naive theoretical expectation and observed reality in all of science, sometimes stated as a difference of around 120 orders of magnitude depending on how the estimate is framed. That number is so large that it stops feeling like a number and becomes a kind of intellectual vertigo. It is as if theory looks at empty space and expects a roaring gravitational ocean, while the universe answers with something almost unbelievably faint. If vacuum energy gravitated as simply as the raw estimates suggest, space should curl, accelerate, or behave in ways utterly unlike the universe we observe. Galaxies, stars, planets, and life would not have developed in anything like the familiar way. Yet here you are, listening, thinking, breathing inside a cosmos whose vacuum energy appears tiny but not zero. That is the cosmological constant problem. Why is the vacuum's gravitational effect so small compared with what our theories seem to imply? And if it is not exactly zero, why does it have this particular small value? This is not a minor technical puzzle hidden in a specialist notebook. It sits at the border between quantum physics and gravity, two of the most successful frameworks ever built, and it exposes a place where their languages do not fit together cleanly. Quantum field theory handles particles and fields with extraordinary precision. General relativity describes gravity and the large-scale structure of space-time beautifully. But when the vacuum energy of quantum fields is allowed to influence space-time through gravity, the result becomes painfully difficult to reconcile with observation. One response is to say that the huge contributions somehow cancel almost perfectly, leaving only a tiny leftover. But that raises another question. Why would the cancellation be so precise? Imagine a balance scale holding mountains on both sides, and after every shift, every hidden weight, every unseen correction, the difference left over is smaller than a grain of dust. You could say the balance happens, but the mind naturally asks why. Is there a deep principle we have not discovered? Is there a symmetry that forces the vacuum energy to cancel? Some proposed ideas, such as supersymmetry, could reduce certain contributions if realized in the right way. But so far, no simple version has solved the problem in the world we observe. Another response is that vacuum energy may be renormalized, meaning that what matters physically is not the raw, infinite-looking sum, but the measured effective value. This is true in many parts of quantum field theory. Calculations are adjusted around observed quantities, and the theory still predicts differences and interactions with breathtaking success. But with gravity, the absolute value of vacuum energy matters because it curves space-time. You cannot simply ignore the baseline in the same easy way because the universe itself responds to it. This is why the problem remains stubborn. It is not merely that we do not know how to calculate a number. It is that we do not yet understand why the number nature uses is so incredibly small and yet apparently not absent. Some physicists wonder whether the answer lies in a deeper theory of quantum gravity, a theory that would explain space-time and quantum fields together rather than forcing them into an uneasy marriage. Others consider whether the cosmological constant is not truly constant, but part of a dynamic field that changes slowly over cosmic time. Others explore anthropic reasoning, suggesting that perhaps only universes with a very small vacuum energy can form galaxies and observers, so we should not be surprised to find ourselves in one of those rare conditions. That idea is controversial, not because it is obviously false, but because it feels different from the kind of explanation science usually wants. It does not show a mechanism as much as a selection effect. It says, in essence, if the value were much larger, no one would be here to ask about it. That may be logically possible, but many physicists still hope for a deeper law rather than a cosmic lottery. And here the topic becomes strangely human. The cosmological constant problem is not only about empty space, it is about the limits of understanding. It shows that science can be extraordinarily successful and still incomplete at its foundations. We can measure the expansion of the universe, map galaxies, detect ancient light, build quantum theories that predict experiments with unbelievable precision, and still be stopped by a quiet question. How much does nothing weigh gravitationally? The word nothing becomes dangerous again, not as philosophy alone, but as a measurable influence on cosmic history. If the cosmological constant is truly vacuum energy, then the smallest background feature of space may help decide the largest fate of the cosmos. It may determine whether expansion keeps accelerating, whether distant galaxies drift beyond view, whether the universe becomes colder, emptier, and more isolated across unimaginable time. A tiny number, almost invisible in local life, becomes a cosmic steering wheel. Yet we should be honest, we do not know the final answer. Anyone who says the cosmological constant problem is solved is either simplifying too much or speaking from a speculative position. The mystery remains open, but this does not make the topic weak. It makes it powerful, because real mystery in science is not ignorance dressed up as wonder. It is a precise wound in our understanding, a place where the best ideas we have fail to meet smoothly. And that wound teaches. It teaches that empty space is not merely a background, that gravity listens to more than matter, that the smallest assumptions can shape the largest conclusions, and that the universe may be balanced on a hidden principle we have not yet learned how to name. So when you hear about vacuum energy and the cosmological constant problem, do not imagine a dry equation sitting in a textbook. Imagine the entire cosmos expanding under the influence of something almost impossibly faint. Imagine physicists staring at the vacuum and realizing that their theories can predict a thunderstorm where nature shows a whisper. Imagine the dark spaces between galaxies carrying a number so small that it lets stars, planets, chemistry, and consciousness exist. And then, let the question settle softly. Maybe the most mysterious thing in the universe is not the brightest explosion, the deepest black hole, or the most distant galaxy, but the quiet fact that empty space seems to have just enough energy to move the cosmos, and far too little for us to understand why. Dark energy. Is empty space stretching the universe? The universe is not exploding outward through darkness. The darkness itself seems to be growing between the galaxies. That single idea is where dark energy begins to feel less like a scientific term and more like a quiet disturbance in the mind, because it asks you to stop picturing the cosmos as debris flying away from a central blast, and instead imagine space itself changing its scale. Galaxies are not mostly racing through space like sparks through air. On the largest scales, the distance between faraway galaxies increases because the fabric of cosmic distance is expanding. For a long time, scientists expected this expansion to slow down. That expectation made sense. Matter has gravity. Gravity attracts. Galaxies, gas, stars, dark matter, all of it should pull on all of it, gently resisting the expansion that began in the early universe. The cosmos might keep expanding forever, or it might slow dramatically, or in older possibilities even collapse again. But acceleration was not the obvious guess. Then, in the late 1990s, astronomers studying distant type Ia supernovae found something deeply surprising. These stellar explosions, useful because their brightness can be used as a cosmic distance marker, appeared dimmer than expected, as if they were farther away than they should have been in a slowing universe. The interpretation was astonishing. The expansion of the universe had not been slowing as expected. It had begun speeding up. Something was acting on the largest scale, not pulling galaxies together, but allowing the distance between distant galaxies to grow faster over time. Scientists gave this unknown cause the name dark energy. The name sounds dramatic, but it is really a label for our ignorance. Dark does not mean evil or shadowy. It means we do not see it directly as light. Energy means it behaves like a component of the universe that affects cosmic expansion. We infer it from what the universe is doing, not because we have bottled it in a laboratory. The simplest model says dark energy may be the energy of empty space itself, something that remains nearly constant as the universe expands. This is very different from matter. If you imagine a group of galaxies inside a growing cosmic volume, ordinary matter becomes more spread out as space expands. Radiation thins out and loses energy as its wavelengths stretch. But if dark energy acts like a constant property of space, then creating more space also means more of that space-like energy exists. This does not mean energy is being produced in the everyday mechanical sense, and it does not behave like fuel pouring into the cosmos. In general relativity, energy, pressure, and expansion are woven together in ways that do not match simple household intuition. The important point is that a component with the right kind of negative pressure can drive accelerated expansion. So when people ask, is empty space stretching the universe? The honest answer is, maybe. In the simplest and most widely used model, dark energy behaves as if empty space has a tiny built-in energy that causes expansion to accelerate on cosmic scales. But we do not know whether that is the final truth. Dark energy could be a cosmological constant, perfectly steady across time. It could be something more dynamic, a slowly changing field sometimes called quintessence. Or it could be a clue that gravity itself behaves differently across enormous distances than our current equations assume. What makes this mystery so powerful is that dark energy is not needed to explain your coffee cup, your room, your body, or the Earth orbiting the Sun. It is not stretching your atoms apart. It is not pulling houses away from streets. Local systems held together by gravity, electromagnetism, and other forces do not expand with the universe in that simple way. The space between the Milky Way and Andromeda, for example, is not expanding fast enough to overcome their mutual gravitational attraction. In fact, those galaxies are moving toward a future merger. Dark energy becomes important across the vast emptiness between galaxy clusters, where local bonds are weak and cosmic expansion dominates. This distinction matters because otherwise the idea becomes a cartoon. The universe is not a loaf of bread making every raisin tear away from every other object at every scale. Bound systems can remain bound. Atoms remain atoms. Solar systems remain solar systems. Galaxies remain galaxies. The acceleration belongs to the largest pattern. The enormous cosmic web seen from far enough away that individual gravitational neighborhoods fade into a broader expansion. And when we look at that broad pattern, dark energy seems to dominate the universe today. Ordinary matter, the kind that makes stars, planets, dust, and people, is only a small part of the total cosmic budget. Dark matter adds much more invisible gravitational structure. But dark energy appears to make up the largest share, guiding the long-term expansion, even though we do not know its inner nature. Evidence for it does not come only from supernovae. The cosmic microwave background, the ancient afterglow of the early universe, helps reveal the overall geometry and contents of the cosmos. The large-scale clustering of galaxies, including patterns called baryon acoustic oscillations, gives another way to trace how expansion has changed over time. Together, these observations form a consistent picture. The universe is expanding in a way that requires something like dark energy. Yet consistency is not the same as full understanding. We can describe the effect with impressive accuracy, but description is not identity. It is like hearing a low note behind a wall and knowing exactly how it changes the music, while still not seeing the instrument. Dark energy may be the quietest dominant thing in reality, powerful enough to shape the fate of the cosmos, subtle enough to leave no ordinary trace in daily life, and mysterious enough to remind us that most of the universe is not built around human intuition. If this acceleration continues forever, distant galaxies not gravitationally bound to us will drift farther and farther away, their light stretched and dimmed, until they eventually become unreachable in practice. Future observers in our local galaxy group might see a much emptier sky and have far less evidence of the wider universe. The cosmos could become lonelier, not because stars vanish immediately, but because expansion hides the distant evidence of its own history. That is the emotional weight of dark energy. It is not only a number in cosmology, it is a slow rewriting of what can be known. It decides how much of the universe remains visible, how far future light can travel to us, how isolated cosmic islands may become across deep time. And still, the most honest sentence remains the most haunting one. We do not know what dark energy really is. We know what it seems to do. We know how it fits our best models. We know the universe behaves as though something with negative pressure is stretching the distances between faraway galaxies faster and faster. But the thing itself remains hidden, silent, unnamed beneath the label. So when you imagine dark energy, do not picture a glowing substance flowing through space like mist. Picture instead a question written into the expansion of the universe. Picture the galaxies as markings on a page whose page itself keeps growing. Picture empty space not as a passive stage, but as something that may carry a faint property capable of influencing the largest future there is. And then, let the strange truth settle gently. The force shaping the destiny of everything may not roar from stars or black holes, but whisper from the space between them. Why empty space may decide the fate of everything. The fate of everything may not be decided by stars, galaxies, or black holes, but by the quiet behavior of the space between them. That is the unsettling possibility hidden inside modern cosmology. The largest ending the universe can have may depend on something that looks, to human eyes, like almost nothing at all. When you imagine the future of the cosmos, your mind probably goes to the dramatic things first: stars exploding, black holes swallowing matter, galaxies colliding in slow motion, civilizations rising and vanishing under alien suns. But on the deepest timeline, those bright events may be secondary. They may be sparks on the surface of a much larger decision being made by empty space itself. The reason is expansion. The universe is not just a collection of objects moving through a fixed background. The distances between faraway galaxies can grow because space itself expands, and the long-term behavior of that expansion decides what the future becomes. If expansion slows, the cosmos has one kind of destiny. If expansion continues steadily, it has another. If expansion accelerates forever, the ending becomes colder, darker, and more isolated than almost anything the human mind can comfortably imagine. And if the cause of that acceleration changes over time, stranger possibilities open. This is why empty space matters. It is not merely the gap between meaningful things. On cosmic scales, the gap may become the main actor. In the simplest current picture, the universe contains something like dark energy, a smooth influence associated with space itself, causing expansion to accelerate. If that influence remains constant, the far future will likely drift toward what is often called heat death. This does not mean the universe burns up. It means the useful differences that allow work, structure, and activity gradually fade. Stars will exhaust their fuel. New star formation will slow as gas is used up or locked away. Galaxies beyond our local gravitational neighborhood will slip farther out of reach, their light stretched and weakened until they become practically invisible. The universe will not end in one dramatic final explosion. It will thin out. It will separate. It will cool. It will become a place where more and more regions are beyond contact, beyond signal, beyond shared history. The terrifying part is not violence, but distance. The cosmos may die not by being destroyed, but by being divided so completely that almost nothing can speak to anything else. Empty space, by growing between things, becomes a kind of slow eraser. It does not erase objects directly. It erases connection. But this is only one possible future, because we still do not know whether dark energy is truly constant. If it changes, the fate of everything changes with it. If dark energy weakens over unimaginable time, expansion might slow, allowing gravity to remain more important in the long run. In some speculative scenarios, the universe could even stop expanding and eventually reverse, moving toward a collapse sometimes called a big crunch. That idea is not the favored simple picture today, but it shows how sensitive cosmic destiny is to the nature of the dark component. A slight difference in how empty space behaves can turn eternal fading into eventual collapse. And if dark energy grows stronger with time, the future becomes more violent. This is the idea behind the Big Rip. In that scenario, expansion accelerates so aggressively that it first pulls galaxy clusters apart, then galaxies, then solar systems, then perhaps even planets, molecules, and atoms. It is a dramatic and speculative possibility, not something we know will happen, but it teaches an important lesson. The expansion of space is not just a background detail. Under the wrong conditions, it could become stronger than the structures that hold the universe together. The fate of matter would then be decided not from inside matter, but by the changing rule of distance itself. There is another layer even deeper than cosmic expansion. The possibility that the vacuum state of our universe may not be the final lowest state. Physicists sometimes discuss false vacuum decay, the theoretical idea that what we call empty space might be stable for an incredibly long time, but not absolutely stable in the deepest possible sense. If the vacuum could transition to a lower energy state, the laws and properties of physics might change in a growing region, expanding outward at nearly the speed of light. This is not a prediction that such an event will happen, and there is no evidence that it is about to happen. It is a theoretical possibility in some kinds of field theory, and it remains highly uncertain, but it reveals how profound the vacuum is in our understanding of reality. Empty space is not merely where the universe happens. It may help define what kinds of particles exist, what forces behave like, what masses particles have, and whether the familiar structure of matter can persist. If the vacuum changed its state, the meaning of everything could change with it. This is why the phrase, "empty space may decide the fate of everything," is not just poetic. It points towards several real scientific possibilities. expansion driven by dark energy, future isolation under constant acceleration, possible changes in dark energy over time, and theoretical questions about vacuum stability. All of these are different, and we must not blend them into one exaggerated myth. Empty space is not a god. It is not choosing. It is not thinking. It has no will, no plan, no hidden intention. But in physics, a thing does not need intention to decide outcomes. Gravity does not intend to shape orbits. Electromagnetism does not intend to hold atoms together. In the same way, the properties of the vacuum may determine the cosmic ending simply by being what they are. That is the strange humility cosmology teaches. The universe does not need drama to be terrifying. A tiny constant, a subtle pressure, a slowly changing field, a hidden stability condition, these quiet ingredients can matter more than all the fireworks in the sky. Your life takes place in the bright age of the cosmos, when stars still burn, galaxies still shine, and the universe still offers enough structure for atoms to form minds capable of asking what comes next. But far beyond that human window, the future may belong increasingly to emptiness. Not emptiness as nothing, but emptiness as the dominant condition. The growing distance, the cooling background, the silent architecture that decides what remains reachable, visible, and alive with possibility. And maybe that is the final emotional turn of the idea. We often think meaning belongs to the things that shine, but the fate of the shining things may belong to the darkness around them. The stars may write the story, but empty space may decide how long the pages stay connected. So when you look into the night sky, do not see only the lights. Notice the distances between them. Notice the quiet. Notice the vastness that seems passive, because that vastness may be carrying the future. The end of everything may not arrive as a roar. It may arrive as expansion, as separation, as a slow fading of contact, as the universe gently becoming too large for itself to remember what it once held together. The Higgs field, the invisible field that gives mass. Somewhere inside the emptiness around you, an invisible field is quietly deciding which particles can move like light and which ones must move more heavily through the world. This is the Higgs field, one of the strangest and most important ideas in modern physics, and it changes the meaning of mass in a way that is easy to misunderstand. When people hear that the Higgs field gives mass, they often imagine a thick, invisible syrup filling space, slowing particles down as they push through it. But that picture is not quite right. The Higgs field is not a cosmic fluid creating friction. It does not drag particles like honey around a spoon. It does not make you heavy in the everyday sense by pulling you toward Earth. Weight comes from gravity. Mass is deeper. It is a measure of how much a thing resists being accelerated, how much it carries an inner reluctance to change its motion. The Higgs field helps explain why some fundamental particles have this kind of rest mass at all. The most remarkable part is that the Higgs field is not just present near matter, or inside stars, or around special machines. It is believed to have a non-zero value everywhere in space, even in what we call vacuum. It is part of the background state of the universe. In the early universe, when conditions were unimaginably hot, the Higgs field may not have acted the way it does now. But as the universe cooled, the field settled into its present state. And that settling changed the identity of many particles forever. Before this transition, in the simplest picture, certain particles would behave as massless. Afterward, because of how they interact with the Higgs field, they gained mass. This is not because the Higgs field grabbed them by the shoulders. It is because particles couple to the field differently, and that coupling shows up as mass. A particle that couples strongly to the Higgs field has more mass. A particle that barely couples has very little. A photon, the particle of light, does not get mass from the Higgs field, which is why light can travel at the universe's speed limit in vacuum. The W and Z bosons, which carry the weak nuclear force, do interact with the Higgs field and become massive, which helps explain why the weak force acts only over extremely tiny distances. The electron also gets its small mass through its relationship with the Higgs field, and that small mass matters enormously. If the electron's mass were very different, Atoms would not have the same size, and chemistry would not unfold in the familiar way. The stability of matter, the shapes of molecules, the possibility of cells, water, DNA, and nervous systems all depend indirectly on these tiny particle masses being what they are. But here we must be careful, because a common oversimplification hides an even deeper truth. The Higgs field does not create most of the mass of your body. Most of your mass comes from protons and neutrons, and most of the mass of protons and neutrons comes not directly from the Higgs field, but from the energy of the strong force binding quarks and gluons inside them. The Higgs field gives mass to quarks themselves, and that still matters. But the heavy substance of ordinary matter is largely the energy of confinement inside atomic nuclei. So the Higgs field is not the whole story of mass. It is the key to why fundamental particles like electrons and quarks have rest mass, and to why the weak force behaves as it does. But the world's weight is built from several layers of physics working together. This makes the truth more beautiful, not less. Reality is not held together by one simple switch. It is a careful stack of hidden mechanisms, each one allowing the next to exist. The Higgs field is one of those mechanisms because it breaks a symmetry that would otherwise make the universe very different. Symmetry breaking sounds technical, but the image is gentle. Imagine a perfectly balanced situation where all directions are equivalent until the system settles into one particular state. Nothing may look violent from far away, but after that settling, the rules experienced by particles are changed. The Higgs field's settled value fills the vacuum like an invisible decision made by the early universe, and every particle that interacts with it carries the consequence of that decision. In 2012, scientists at CERN announced the discovery of a particle consistent with the Higgs boson, a ripple or excitation of the Higgs field. This was not the same as seeing the field directly with human eyes. It was more like striking the field hard enough in a particle collider to make a brief detectable echo, then reconstructing that echo from the particles it decayed into. The discovery mattered because it confirmed the last missing piece of the standard model of particle physics, the framework that describes the known fundamental particles and 3 of the fundamental forces with remarkable success. But the Higgs boson itself is not the field in its everyday presence. It is a detectable excitation of the field, a sign that the field is real enough to be disturbed. The deeper presence of the Higgs field is quieter than the famous discovery event. It is not flashing inside space. It is not glowing behind atoms. It is simply part of the vacuum structure, so constant and so deeply woven into physics that you never notice it, just as you do not notice the rules of grammar while speaking unless something breaks. And that is what makes the Higgs field so haunting. It suggests that mass, one of the most basic features of the objects around you, is not merely stuffness, it is relationship. A particle's mass can depend on how it relates to an invisible field that fills the universe. The solidity of your hand, the resistance of a stone, the chemistry of your body, the lightness of the electron, the short reach of the weak force, all of these are connected to a hidden field whose presence is everywhere and whose effect is different for different particles. The world feels obvious because its foundations are stable, but stable does not mean simple. Beneath every familiar object is a universe that had to settle into the right kind of vacuum for familiar matter to exist at all. If the Higgs field had settled differently, the masses of particles might be different. Atoms might not hold together in the same way, stars might burn differently or not at all, and the story that led to you might never have found a path. So when you hear that the Higgs field gives mass, do not imagine a magical fog pressing on particles. Imagine something stranger and more disciplined, an invisible field present across space, a deep property of the vacuum, a quiet relationship that turns certain fundamental particles from massless possibilities into the ingredients of a structured universe. You do not feel the Higgs field as a breeze. You do not see it as a color. Yet without its settled presence, the physical world would lose part of the grammar that lets matter become matter. And maybe that is the softest shock of all. What gives things some of their heaviness is not a visible substance inside them, but an unseen field everywhere around them, so ordinary in its constancy that the universe can build stars, atoms, bodies, and questions upon it without ever needing to announce that it is there. Why mass may come from fields, not solid stuff. The heaviness of your body may not come from tiny pieces of solid stuff, but from invisible fields holding energy in patterns that refuse to fall apart. This is a difficult idea to feel at first, because everything around you teaches the opposite. A stone feels heavy because it seems packed with material. A metal bar feels dense because it seems full of hard substance. Your body has weight because it seems made of flesh, bone, water, and atoms, all stacked together like microscopic bricks. But modern physics slowly removes that comforting picture. It shows that matter is not built from little solid grains in the way a wall is built from stones. At the deepest levels we can currently describe, the things we call particles are tied to fields, and the mass of ordinary objects is not simply the sum of tiny hard beads. Much of it comes from energy trapped in field activity, especially inside protons and neutrons. This is one of the most surprising truths in physics. Most of the mass of the matter you touch is not directly the mass of the small quarks inside protons and neutrons. Those quarks do have masses, and those masses matter, but they account for only a small fraction of the proton's total mass. The larger part comes from the energy of the strong force field, from the motion and confinement of quarks and gluons inside the proton and neutron. In other words, a proton is not a little solid ball with 3 tiny stones inside. It is a turbulent, tightly bound quantum system, a storm of fields whose energy contributes to its mass. That sounds almost poetic, but it is real physics. Einstein's famous insight that mass and energy are deeply connected means energy can contribute to inertia, to the resistance an object has when you try to accelerate it. So when energy is trapped inside a stable system, it can show up as mass. A hot object weighs a tiny bit more than a cold version of the same object because it contains slightly more energy, though the difference is far too small to notice in daily life. A compressed spring has slightly more mass than an uncompressed one because stored energy counts. A bound atomic nucleus can have less mass than its separated parts because energy has been released in binding it together. These are not tricks of language. They are reminders that mass is not just amount of stuff. It is a property of a system's total energy and structure. This is why the phrase solid stuff can mislead you. Solidity is how large collections of atoms resist your hand, mostly through electromagnetic interactions and quantum rules. But mass, at a deeper level, can arise from fields, motion, binding, and energy. The world feels like substance because its underlying patterns are stable enough to push back. A table does not let your hand pass through it because its atoms and electrons obey physical rules that create resistance, not because the table is filled with tiny pieces of ultimate hardness. If you zoom down far enough, the hard surface disappears into atoms, then into nuclei and electrons, then into quantum fields and forces. The stuff becomes less like gravel and more like organized activity. This does not make the table less real. It makes reality less primitive than your senses suggest. The mass of a proton, for example, is not a simple object weight in the old intuitive sense. Quarks inside it are never found alone under ordinary conditions, because the strong force confines them. The harder you try to pull them apart, the more energy the field stores, until new particles can form instead of freeing a single quark. This confinement is one reason the proton has a stable identity, and the energy involved is a major source of its mass. Your body, then, is heavy, mostly because atomic nuclei contain protons and neutrons whose masses are dominated by strong field energy. The everyday weight you feel when you stand up, carry a bag, or lift your arm is connected to this hidden field energy locked inside matter. That is astonishing. The heaviness of your bones is not mainly the heaviness of tiny solid pellets. It is the heaviness of energy bound into stable quantum structures. And this also explains why mass is not one single story. Some fundamental particles have rest mass through their interaction with the Higgs field. Composite particles like protons get most of their mass from the energy of the strong interaction. Atomic nuclei gain or lose mass depending on binding energy. Whole objects carry additional mass from heat, motion, stress, chemical energy, and internal structure, though these changes are usually incredibly small compared with the object's total mass. Mass is layered. It is not a simple substance poured into things. It is a record of how energy is arranged, confined, and made stable. Once you see this, matter becomes more mysterious but also more understandable. You stop imagining the universe as a pile of hard particles and begin to see it as patterns of fields that have learned how to persist. A particle can be stable. A nucleus can hold together. An atom can keep its shape. A molecule can build life. A body can stand under gravity. But beneath all of this is not simple solidity. It is structure. It is relationship. It is energy held in forms that resist change. And perhaps that is the deeper lesson. What feels most solid in your life may not be solid in the way it appears. The floor beneath you, the blood in your veins, the hand you raise in front of your face, all of it is built from patterns so stable that they feel like objects, from fields so invisible that they feel like nothing, from energy so deeply bound that it feels like mass. Physics does not take the world away when it says this. It gives the world back with more depth. You are not made of dead little chunks of stuff. You are made of organized field energy, of forces holding form, of invisible structures strong enough to become atoms, cells, memory, breath, and awareness. The heavy world is real, but its heaviness may come not from ultimate solid matter, but from the quiet power of fields arranged in ways that endure. How empty space can behave differently in different conditions. The vacuum is not one unchanging emptiness. Under different conditions, it can behave like reality has quietly changed the rules of the room. This is a strange thought, because we are used to treating empty space as the same everywhere, as if the absence of matter should have no personality, no history, no sensitivity to its surroundings. A clean vacuum in a laboratory, the space between planets, the region near a neutron star, the early universe shortly after the Big Bang, and the space near a black hole horizon can all be called empty in some sense. Yet physics does not always treat them as identical. The word vacuum does not simply mean nothing is there. More carefully, it means the lowest available state of a physical system under the conditions being considered. And that phrase, under the conditions, changes everything. A quiet room is not the same as silence inside a cave, or silence underwater, or silence in a recording studio, because the environment decides what silence means. In a similar way, the vacuum depends on the fields present, the temperature, the boundaries, the gravity, the motion of the observer, and the history of the universe itself. This does not mean empty space is alive or moody. It means the vacuum is a physical state, and physical states can depend on context. At ordinary human scales, the vacuum near Earth behaves in a stable and familiar way. Light moves through it in a predictable manner. Particles have their usual masses and charges, and the laws of physics appear calm enough for atoms, chemistry, planets, and bodies to exist. But near extreme objects, the story becomes less simple. Around magnetars, which are neutron stars with magnetic fields far beyond anything we can produce in ordinary laboratories, the electromagnetic conditions are so intense that the quantum vacuum is expected to respond in ways that would be undetectable here on Earth. It may slightly affect the polarization of light, revealing that the vacuum under extreme fields can act less like a perfectly neutral stage and more like a delicate medium with hidden structure. This does not turn the vacuum into glass in the everyday sense, and it does not mean space becomes thick or touchable. It means that fields strong enough can expose tiny effects that are normally too faint to matter. The same empty-looking space becomes scientifically different because the conditions have changed. Temperature also matters. In the very early universe, the cosmos was hot, dense, and energetic in a way that is almost impossible to imagine. Under those conditions, the vacuum state of fields may not have been the same as it is today. As the universe cooled, fields could settle into new arrangements, and these changes help shape the particles and forces we now take for granted. This is one reason the early universe is not just a smaller, hotter version of the present universe. It may have passed through transitions where the underlying field states changed. A little like water changing from vapor to liquid or liquid to ice, though the comparison is only an analogy. The deeper point is that empty space at one temperature can be physically different from empty space at another. What counts as the lower state of the fields can shift. What seems natural now may not have been the same in the young cosmos. The vacuum has a history. It may carry the memory of how the universe cooled into its present form, not as a story written in words, but as a set of field values and physical properties that allow the world to behave as it does. Motion can also change how the vacuum is experienced. There is a remarkable idea called the Unruh effect, which says that an observer accelerating through what an inertial observer calls vacuum would, in principle, detect something like a faint warmth, a bath of particles associated with that acceleration. This effect is extraordinarily tiny for ordinary accelerations, so it is not something you would notice in daily life, and detecting it directly is extremely difficult. But conceptually, it is profound. It suggests that what one observer calls empty may not be described in exactly the same way by another observer moving differently. Emptiness is not always an absolute statement shared by every possible viewpoint. In some situations, vacuum depends on the observer's motion through space-time. That does not mean reality becomes subjective in a loose or magical way. It means that quantum fields and relativity together make the idea of no particles more subtle than common sense expects. A vacuum is not merely a container with all objects removed. It is defined relative to the way fields are measured, and measurement itself can depend on motion and geometry. Gravity adds another layer. Near a black hole, space-time is curved so strongly that the meaning of particles and vacuum becomes more complicated than in flat, quiet space. This is connected to the idea of Hawking radiation, where black holes are predicted to emit a faint thermal radiation because of quantum field effects in curved space-time. The simplified popular picture often speaks of particle pairs at the horizon, but the deeper lesson is that a gravitational horizon changes how the vacuum is defined and how observers describe field states. Again, the important point is not fantasy. It is that the vacuum is not one simple universal emptiness that looks the same under all conditions. The geometry of space-time itself can influence what the vacuum means. Boundaries matter too, though not only in the familiar example of plates. A tiny cavity, a mirror arrangement, a material surface, or a specially structured environment can restrict which field patterns are available in a region. This can change how atoms emit light, how forces appear at small separations, or how delicate quantum systems behave. The vacuum inside a carefully shaped cavity is not identical in its practical effects to the vacuum far from all surfaces. The emptiness has been given a shape, and shape can change possibility. That is a quiet but powerful idea. Conditions do not need to fill space with ordinary matter in order to change what fields can do. The rules available in a region can be altered by boundaries, motion, temperature, gravity, and strong external fields. And maybe this is why the vacuum feels so difficult to understand. We want emptiness to be the simplest thing, the one part of reality with no details left. But physics keeps showing us that empty can mean different physical states depending on the situation. There may be a vacuum state for one field arrangement, another effective vacuum in a hot environment, another description for an accelerated observer, another behavior near intense gravity, another set of allowed patterns near boundaries. This does not make science weaker, it makes it more precise. Instead of using one vague word for every kind of absence, physics asks, absence relative to what? Under what conditions? For which observer? In which field state? With what boundaries? At what temperature? Near what gravitational geometry? The answers matter because the vacuum is not a blank nothing behind the universe. It is part of the universe's structure. It can be calm in one setting and subtly responsive in another. It can look empty to one observer and carry thermal meaning to another. It can allow one set of particle properties in the present universe and perhaps a different set in the early universe. It can be shaped by mirrors, stretched by cosmic history, disturbed by extreme fields, and complicated by horizons. And yet through all of this, we must keep the wonder honest. The vacuum is not a magical substance changing moods. It is not consciousness. It is not intention. It is a physical state defined by the conditions around it. That is enough. The real universe does not need exaggeration to become astonishing. The fact that emptiness has conditions is already a deep shock. So when you imagine empty space, do not picture one universal blankness spread everywhere, like a perfect sheet of darkness. Imagine instead a quiet field of possibilities whose behavior depends on where it is, how it is shaped, how it moves, how it has cooled, and what kind of space-time it inhabits. The vacuum may be the closest thing physics has to emptiness, but it is not a single featureless silence. It is a silence with context, and once you understand that, the universe becomes less like objects placed inside nothing, and more like a vast, changing structure where even the absence of things has a history, a condition, and a role in what reality is allowed to become. False vacuum. Could space have a hidden lower state? What if the space around you is stable only in the way a ball is stable when it rests in a shallow valley? Not at the deepest point in the landscape, but in a dip high above a lower place it has not yet reached. This is the idea behind a false vacuum, and it is one of the most unsettling possibilities in modern physics, because it suggests that what we call empty space may not be the final, most secure state of reality. To understand it, begin with a simple image, but hold it carefully. Imagine a wide landscape of hills and valleys. A ball rolls down a slope and settles into a valley. From nearby, it seems safe. It is not moving. It looks finished. If you only looked at that valley, you might think the ball had reached the bottom of everything. But far away, hidden beyond a ridge, there may be a deeper valley. The ball is stable where it is, but not absolutely stable. It is trapped in a local resting place, not the lowest possible resting place. A false vacuum is something like that, except the ball is not an object, and the landscape is not made of dirt or stone. It is a way physicists describe possible states of fields that fill space. A true vacuum would be the lowest possible energy state, the deepest valley. A false vacuum would be a state that appears stable because there is a barrier preventing it from easily changing, even though a lower energy state exists somewhere beyond that barrier. In ordinary life, if something is trapped behind a barrier, it needs enough energy to climb over. But in quantum physics, there is also the possibility of tunneling, where a system can transition through a barrier in a way that has no everyday equivalent. This does not mean anything can happen at any time for no reason. It means quantum fields can, in principle, move from a metastable state to a lower state with some probability, even if the classical path seems blocked. The word metastable is important. It means stable for a very long time, perhaps far longer than the age of the universe, but not guaranteed in the absolute deepest sense. The reason this matters for our universe is that fields are not just background decorations. Their vacuum states can help define the properties of particles and forces. If the vacuum state changed, the rules experienced by matter could change with it. Particle masses, interactions, and the structure that allows atoms and chemistry to exist might no longer be the same. This is why false vacuum decay sounds so terrifying when described dramatically. If a tiny region of space tunneled into a lower energy vacuum, it could form a bubble of true vacuum that expands outward at nearly the speed of light, converting surrounding space as it grows. Inside that bubble, the laws of physics as we know them might be different. Matter might not hold together. Stars, planets, atoms, and living systems might not survive in recognizable form. But here, honesty is essential. This is not something scientists believe is about to happen. There is no evidence that a vacuum decay event is near. And if our current understanding points toward metastability, the expected lifetime of the vacuum is usually calculated to be enormously, unimaginably longer than the current age of the universe. The real scientific interest is not panic. It is understanding whether the vacuum state of our universe is absolutely stable, metastable, or something else we have not yet fully grasped. Measurements of the Higgs boson and the top quark are especially important here because they influence how physicists estimate the shape of the Higgs field's potential at very high energies. In the Standard Model, as we currently understand it, using the measured values we have, the vacuum may sit close to the boundary between stability and metastability. That is remarkable. It suggests the universe may not be obviously deep in the safest possible valley, but near a delicate dividing line. However, the conclusion depends on precise measurements and on whether new physics appears at energies we have not yet explored. The Standard Model is powerful, but many physicists do not believe it is the final theory of everything. Gravity is not fully integrated into it. Dark matter is not explained by it. Neutrino masses point beyond its simplest form. So when people say our vacuum may be metastable, they are speaking within a framework that could be changed by deeper physics. A new field, a new particle, or a more complete theory at extremely high energies could alter the whole conclusion. That uncertainty should calm the sensational version of the story, but it should not erase the wonder. The false vacuum idea teaches that empty space is not simply emptiness. It may have phases like matter has phases. Water can be ice, liquid, or vapor depending on conditions. A magnet can change its internal order with temperature. Materials can suddenly shift from one state to another when the right threshold is crossed. In field theory, the vacuum can also be thought of as having possible states. The universe we inhabit may be one particular state among several possible states of the underlying fields. And if that is true, then the properties of reality are not merely there in a timeless, obvious way. They are the result of the state the fields have settled into. The electron has its mass, forces have their strengths, atoms behave as they do, because the vacuum has the structure it has. Change that structure, and the meaning of matter could change. This makes the ordinary world feel suddenly conditional. The table in front of you, the light in your room, the rhythm of your breathing, the chemistry inside every cell, all depend on the vacuum remaining in the state that supports them. Yet this should not make the world feel fragile in a cheap way. A mountain can be stable for millions of years and still not be eternal. A star can burn reliably for billions of years and still one day exhaust its fuel. Stability does not have to mean forever to be real. The vacuum may be stable on timescales so vast that human fear has no useful scale for them. The lesson is not that disaster is waiting around the corner. The lesson is that reality has depth beneath its calm. The universe may have hidden structure even in its quietest foundation. What looks like the final floor may be one shelf in a deeper architecture. And perhaps that is why the false vacuum is so philosophically powerful. It forces you to ask whether the laws of physics are fixed like commandments or more like the behavior of a system in a particular state. It asks whether the emptiness that surrounds every galaxy, every atom, and every thought is truly at the bottom of possibility, or only resting in a long-lived valley. It asks how much of what feels inevitable is actually contingent, how much of existence depends on the vacuum not changing its mind, though of course it has no mind at all. Physics strips away intention, but not mystery. A false vacuum would not decay because it wants to. It would decay because the structure of fields allows a lower state, and because quantum transition is possible in principle. That is colder than myth, but deeper than myth too. So when you hear the phrase false vacuum, do not imagine fake space or an illusion you can see through. Imagine a universe whose emptiness may be stable but not necessarily final, a silence that may be resting above a deeper silence, a reality whose most familiar laws may depend on an invisible field configuration spread everywhere. And as strange as it sounds, the comfort is this: the very fact that the universe has lasted long enough for stars, planets, life, memory, and questions to appear tells us that this vacuum, whatever its ultimate status, is extraordinarily durable. You are not living on a cracking floor. You are living inside a cosmic state that has endured for nearly 14 billion years, quietly holding the rules steady enough for matter to become aware of them. The false vacuum is frightening only if you treat it as a prophecy. Seen honestly, it is something more profound, a reminder that even empty space may have hidden depths, and that the stability of everything may come not from absolute certainty, but from a long, silent balance the universe has kept since the beginning: vacuum decay and the most terrifying theoretical possibility. The most terrifying end in physics would not arrive with a sound, a warning, or a sky turning red. It would arrive as a new kind of space rewriting the old one before anything inside it could understand what had happened. This is the idea of vacuum decay, one of the strangest theoretical possibilities ever considered. And it is frightening not because scientists expect it tomorrow, but because it shows how deeply the universe depends on the hidden state of what we casually call emptiness. To understand it, you have to imagine that empty space is not merely a background, but a physical condition with its own stability. In our universe, the fields that fill space seem to sit in a state that allows particles to have the properties they have: atoms to hold together, stars to burn, chemistry to work, and life to exist. But in some theories, the vacuum we live in might not be the absolute lowest possible state. It may be stable in practice, yet not the deepest state available in principle. If that is true, then somewhere, under conditions we do not control and may never observe directly, a tiny region of space could theoretically transition into a lower energy vacuum state. That tiny region would be like a seed of different physics. It would not be a bomb in space. It would not be fire spreading through air. It would be more fundamental than that. A bubble of vacuum with different field values, expanding outward and converting the old vacuum into the new one. The edge of that bubble would move at nearly the speed of light, which means there would be no meaningful warning. You could not see it coming, because any signal from it would arrive no earlier than the bubble itself. One moment, the laws of physics around you would be the laws you know. The next, they might no longer support the structures that made you possible. This is why vacuum decay is often called terrifying. It is not terrifying like an asteroid, where there is a trajectory to calculate, a telescope to point, a mission to plan. It is terrifying because it belongs to the level beneath objects, beneath stars, beneath matter as familiar form. If the vacuum state changed, the basic rules experienced by particles could change too. The masses of particles might be different. Forces might behave differently. Atoms might no longer be stable. Chemistry could become impossible. The new vacuum would not need to destroy things in the ordinary sense, because the category of thing might stop working the way it does now. A chair, a planet, a cell, a memory, a human hand, all depend on the same underlying field conditions remaining steady. Change those conditions deeply enough, and the universe would not break like glass. It would stop being the kind of universe in which glass can exist. But this is where honesty matters more than drama. Vacuum decay is not a known future event. It is not a confirmed destiny. It is not something anyone has detected beginning. It is a theoretical possibility that appears in certain ways of thinking about fields, especially when physicists ask whether our vacuum is absolutely stable or only metastable. Current evidence suggests our universe has survived for nearly 14 billion years without such a transition, and calculations that consider metastability often suggest lifetimes vastly longer than the present age of the cosmos. Also, high-energy particle collisions created by humans are not thought to pose this danger. Nature has been running far more energetic collisions for billions of years, when cosmic rays strike planets, stars, and dense astrophysical objects. If ordinary high-energy collisions could easily trigger vacuum decay, the universe would likely have revealed that danger long before humans built accelerators. This is important because fear spreads faster than understanding. The correct response to vacuum decay is not panic. It is humility. It reminds us that some of the deepest questions in physics are not about what happens inside space, but about what space itself is allowed to be. The process, if it were possible, would begin through something called quantum tunneling, where a field can transition through an energy barrier rather than climbing over it in the ordinary classical sense. That phrase can sound mystical, but it is a real feature of quantum theory, seen in many less catastrophic systems. In vacuum decay, the idea is taken to its most extreme cosmic form. A field trapped in a long-lived state might eventually tunnel into a lower one. The transition would create a bubble, and if the lower vacuum is truly favored, the bubble could expand. But the details depend on physics we do not fully know. The standard model gives one kind of picture, yet the standard model is not the final word on reality. It does not fully include gravity as a quantum theory. It does not explain dark matter. It leaves open many questions about the early universe. New physics at higher energies could make the vacuum more stable, less stable, or change the story completely. So vacuum decay is not a prophecy carved into the cosmos. It is a question mark at the bottom of the map. And maybe that is why it is so powerful for the mind. It forces you to separate fear from truth. The fear says, everything could vanish without warning. The truth says, we have a theoretical framework in which vacuum stability can be studied, but no evidence of imminent decay, and many reasons not to turn the idea into alarm. The fear says, the universe is unsafe. The truth says, the universe has been stable long enough to form galaxies, stars, planets, oceans, cells, minds, and the very science that can ask whether it is stable. That is not a guarantee of eternity, but it is a profound fact. The cosmos has held its rules together across deep time. Every sunrise is evidence of that stability. Every atom in your body is a quiet vote for the vacuum's endurance. Still, the idea leaves a mark because it reveals how conditional everything is. You may think of reality as solid because the ground feels firm, because light behaves predictably, because matter keeps its shape, because time seems to pass with familiar rhythm. But beneath all of that is a vacuum state whose properties make the familiar possible. The terror of vacuum decay is really the terror of realizing that the laws of nature are not floating above the universe like eternal instructions separate from existence. They may be tied to the state of the fields themselves. What you call reality may be a phase of something deeper, and if phases can change, then even the most basic conditions may have a history, a structure, and perhaps a vulnerability. Yet there is also a strange calm hidden inside this thought. If the universe is metastable, it is metastable on a scale so immense that human life is a breath inside its patience. The possibility does not ask you to live in fear. It asks you to understand how precious stability is. It asks you to see every ordinary moment as something supported by invisible agreement. The electron staying itself, the photon behaving as light, the forces keeping their strengths, the vacuum holding its shape. Vacuum decay may be the most terrifying theoretical possibility, but it is also one of the clearest reminders that existence is not a simple default. It is a balance, a state, a deep arrangement that has lasted long enough for the universe to become aware of its own fragility. So when you hear the phrase, do not imagine a monster waiting in space, imagine the edge of human understanding, where physics looks beneath matter and finds that even emptiness has a stability question. Imagine the quiet courage of science, willing to study a possibility too vast to feel comfortable, and then return gently to the room around you, to the light, to the air, to the atoms holding their form, and notice the miracle that nothing has changed. The vacuum remains, the laws remain, the world continues, and for now that silent continuity is the deepest comfort the universe offers. Why space is not a passive background. Space is not the empty stage where the universe performs. It is part of the performance itself. This is the quiet revolution hidden beneath modern physics. Because for most of human history, we imagine space as a kind of invisible container, a vast nothing that simply held planets, stars, light, and motion. In that older picture, space was passive. It did not act. It did not respond. It did not carry history. It was the silent room in which matter moved, the background grid against which events could be measured. But the deeper we looked, the more that simple picture began to break. Space turned out not to be a dead emptiness behind reality, but something with structure, geometry, and physical consequences. The first great crack came from Einstein's general relativity, which showed that gravity is not best understood as an invisible force pulling objects through a fixed arena. Instead, matter and energy shape space-time, and space-time shapes the motion of matter and light. A planet orbiting a star is not merely being tugged through a static void. It is following the curved geometry created by the star's presence. Light passing near a massive galaxy can bend, not because the galaxy reaches out like a hand, but because the path through space-time itself has changed. This means space is not simply where gravity happens. Space, together with time, is part of what gravity is. It can curve around stars, ripple after violent cosmic collisions, stretch across the universe, and carry gravitational waves like faint tremors moving outward from black hole mergers. These waves are especially important because they show that space-time is not just a mathematical idea written on a board. It can be disturbed. It can transmit changes. When two black holes spiral together and merge, they send ripples through space-time that can cross billions of light years and slightly change the distance between mirrors in detectors on Earth by less than the width of a proton. That tiny change is not the detector imagining something. It is space itself responding to an event long ago and far away. A passive background would not ripple. A passive background would not bend light. A passive background would not expand. Yet our universe does all of these, and expansion may be the clearest sign that space is not merely a container. Galaxies on very large scales are not simply flying through space like fragments from an explosion. The distances between distant galaxies grow because space itself expands. The universe is not expanding into an outside room. The room-like relationship between faraway regions is changing. This is difficult to picture because your mind wants every expansion to happen into something larger. A balloon expands into the air around it. Smoke expands into a room. But cosmic expansion is stranger. It is not matter moving into pre-existing emptiness, but the scale of emptiness itself changing. Space is dynamic. It can grow. It can carry the history of that growth in the stretched light from distant galaxies. It can decide which regions remain reachable and which drift beyond cosmic horizons. That is not passive. That is architectural. On smaller scales, quantum physics adds another layer. Space is not just a geometrical idea. It is also the setting in which fields exist everywhere, and those fields define what particles can be. This does not mean space is a substance like water, and it does not mean it has a hidden mind. But it does mean that the absence of visible objects is not the absence of physical structure. A region can be empty of atoms and still have field states, boundary conditions, possible excitations, and measurable effects. The vacuum can influence how atoms release light, how tiny surfaces feel forces, how particles interact, and how precision measurements come out. So the background is not blank. It participates through the rules it carries. In some cases, even the shape of the surrounding space matters. A cavity, a mirror, or a surface can alter what field patterns are possible nearby, and that can change the behavior of matter placed there. In curved spacetime, the idea of particles itself can become observer-dependent, showing that what counts as empty is not always a simple universal statement. This does not destroy reality. It refines it. It tells us that space is not an invisible box with fixed labels. It is part of the physical situation. And perhaps the most profound reason space is not passive is that it sets the stage for causality. The structure of space-time tells events what can influence what. Nothing with information can outrun light in vacuum, not because light is special as a glowing thing, but because space-time has a causal structure. There are regions you can affect and regions you cannot. There are events whose light can reach you and events forever outside your horizon. The shape and expansion of space decide the boundaries of knowledge. You do not see the whole universe, not because your telescope is weak, but because space-time itself limits what can be seen. The observable universe is not the entire universe. It is the region from which light has had time to reach us since the beginning of cosmic history. That boundary is not a wall. It is a consequence of space, time, and the finite speed at which influence travels. In this way, space is not only geometry, it is permission. It decides which events can touch each other across time. And this should change the emotional feeling of the emptiness around you. The gap between your hand and a distant star is not a dead interval. It is a structured distance through which light travels, gravity curves, fields exist, and time gives events order. The The space inside a room is not visually dramatic, but it is still part of the physical world that allows motion, separation, measurement, and relationship. Without space, objects would not merely be crowded together. The meaning of together and apart would disappear. Without space-time, cause and effect would have no arena in which to unfold. Without geometry, gravity would not have its modern language. Without expansion, cosmic history would look nothing like the universe we observe. This does not mean space is material in the ordinary sense. You cannot scoop it into a jar. You cannot touch it like fabric, even though the phrase fabric of space-time is useful as a metaphor. The danger is taking that metaphor too literally. Space is not cloth stretched across a cosmic table. It is a physical structure described by geometry and fields. And our language struggles because it was built for hands, surfaces, and everyday objects. But even when language fails, the lesson remains clear. Space does things. It bends paths. It stretches wavelengths. It carries ripples. It defines horizons. It shapes what the vacuum means. It gives gravity its form. It is not merely the absence of objects, but one of the conditions that allows objects to exist and interact at all. And maybe that is the softest shock of this idea. You have lived your whole life inside space without noticing it, the way you live inside time without seeing it. You notice the furniture, not the room. You notice the stars, not the distances. You notice the object, not the geometry that lets it have a place. But physics asks you to look again at the invisible frame and realize it was never just a frame. It was active, responsive, and woven into the behavior of everything. The universe is not matter moving through nothing. It is matter, energy, fields, space, and time shaping one another in a single unfolding story. So when you stare into a dark sky and see what looks like emptiness, remember that you are not looking at a passive background. You are looking into a physical reality that can curve, expand, ripple, and limit what can ever be known. Space is quiet, but it is not idle. It is silent, but not absent. It does not speak in words. But every orbit, every beam of light, every gravitational wave, every distant galaxy drifting beyond reach is part of its language. How quantum fields replace the old idea of particles. The old idea of a particle dies slowly, not because it was useless, but because the universe turned out to be too deep for tiny solid dots. For centuries, the particle picture felt almost irresistible. Matter looked as if it must be made from smaller and smaller pieces, like a wall made from bricks, a beach made from grains, a body made from cells, and cells made from molecules. If you could only zoom in far enough, the hope was that you would eventually find the final little objects, the smallest beads of reality, hard and definite, moving through space according to clear rules. This picture worked beautifully for many things. It helped explain gases, collisions, chemistry, and the rough behavior of matter. Even today, scientists still speak of particles because the word is useful. Detectors register sharp events, instruments count arrivals. A photon hits a sensor. An electron leaves a track. A proton collides, something localized happens, and calling it a particle is often the cleanest way to talk. But the deeper theory does not treat these particles as tiny classical balls. It replaces that old image with something stranger. Fields as the primary reality, and particles as the measurable events or excitations that appear when those fields take on certain states. This replacement did not happen because physicists wanted a more poetic universe. It happened because the old picture could not survive the evidence. The first crack came when light refused to be either purely wave or purely particle. Then electrons, which seemed like little bits of matter, began producing wave-like interference under the right conditions. Then quantum mechanics showed that small things do not always have definite properties before measurement in the way everyday objects appear to. Then special relativity added another demand. Any deep theory of matter must respect the fact that no signal outruns light, and that energy can become matter under the right conditions. When quantum theory and relativity were brought together, the old particle picture became too rigid. A fixed number of little objects moving through space was not enough. In high-energy processes, particles can be created and destroyed. An energetic photon near a nucleus can produce an electron and its antimatter partner. A particle can decay into other particles. Collisions can turn motion and field energy into new detectable matter. If particles were the ultimate permanent building blocks in the old sense, this would be hard to understand. But if fields are fundamental, then particle creation is not magic. It is a field changing its state. A particle is not a tiny eternal pebble pulled from nowhere. It is a quantized excitation, a specific way a field can carry energy and other properties. This is why quantum field theory became the language of the Standard Model, the best tested framework we have for the known elementary particles and their interactions. In that language, there is an electron field spread through the universe, and every electron is an excitation of that one field. This also explains something deeply strange that the old particle picture struggles with. All electrons are identical, not just similar, not just made in the same factory, but truly indistinguishable in every measured intrinsic property. The electron in your body and an electron in a distant star are not two handcrafted objects that happen to match. They are excitations of the same underlying electron field. Their sameness is not a coincidence. It is a clue. In the field view, nature does not need to manufacture separate little identities for each electron. The field is universal, and the excitations of that field carry the same properties wherever they appear. This is a quiet but enormous change in worldview. Reality becomes less like a collection of tiny named objects and more like a set of invisible systems capable of producing repeated, identical appearances. It also changes how forces are understood. In the old image, one particle somehow reaches across empty space and pulls or pushes another. In the field view, interactions happen because fields are coupled to one another. Charged particles interact through the electromagnetic field. Quarks interact through the strong force fields. The weak interaction has its own carriers. The Higgs field gives certain particles their rest mass through their relationship with it. The universe becomes a network of fields, each with its own rules, each able to influence others, each producing what we detect as particles when conditions allow. But this does not mean the word particle should be thrown away. A particle is still real as an observed event, just as a wave on the ocean is real, even though it is not separate from the ocean. The mistake is to think the particle is a tiny classical object with a fixed little surface, moving like a miniature planet through a microscopic solar system. Quantum fields replace that picture with one where the thing you detect is the local expression of a deeper, extended reality. A detector does not usually see the whole field. It registers a click, a track, a deposit of energy. Your instruments meet the field through events, and those events look particle-like. This is why the modern view can feel paradoxical. Fields are spread out, but detections are localized. The theory beneath the surface is continuous in one sense, yet the outcomes come in discrete packets. Nature is not choosing between wave and particle in the old, simple way. It is showing you different faces of a deeper framework. Even empty space changes meaning here. In a purely particle-based universe, empty space would be the absence of all objects. In a field-based universe, the vacuum is the lowest state of the fields, not the deletion of the fields themselves. The fields remain, their possible excitations remain, their rules remain. This is why the vacuum can have subtle effects, why boundaries can change field behavior, why particle interactions can be calculated with such precision even when no little mechanical gears are visible. The field picture also helps explain antimatter. For every electron, there is a positron, the electron's antimatter counterpart. In quantum field theory, particles and antiparticles arise naturally from the structure of fields that respect relativity. Antimatter is not an afterthought or a fantasy mirror world. It is part of the same field language. The old idea of particles as standalone beads could describe some behaviors, but it did not naturally reveal why such counterparts should exist. Fields made the pattern clearer, and perhaps the most important shift is philosophical as much as scientific. The basic level of the universe may not be things at all, but organized possibilities for events. A particle becomes less like a noun and more like a happening. Matter becomes less like a pile and more like a pattern. Solidity becomes the large-scale result of fields, charges, quantum rules, and stable arrangements. Your hand feels continuous, but it is built from atoms. Atoms are built from quantum states. Nuclei are built from quarks and gluons whose mass comes largely from field energy. The light touching your eyes is excitation of the electromagnetic field. The electrons shaping chemistry are excitations of the electron field. The familiar world is what field behavior looks like after it has been organized into stable forms. This does not make reality vague. It makes it more precise than the old picture allowed. Quantum field theory is not a loose metaphor. It is a mathematical framework that has predicted experimental results with astonishing accuracy. But for the mind, its lesson is gentle and unsettling. The universe may not be made from tiny solid pieces at the bottom. It may be made from fields whose excitations appear as pieces when measured. The particle is not erased. It is redefined. It becomes a visible crest, not the whole sea. It becomes the footprint, not the entire animal. It becomes the note you hear, not the instrument that made it possible. And when you let that idea settle, the world around you begins to change without moving. The table is still there. The air is still there. Your body is still there. But beneath their familiar presence, reality is no longer a silent warehouse of objects. It is an active field structure, a layered music of invisible systems, where what we call particles are the moments the music becomes sharp enough to count. The old particle picture gave us a universe made of little things. Quantum fields give us something stranger, a universe where the deepest things may be the fields themselves. And everything solid is what happens when the invisible learns how to appear. The difference between empty space and outer space. Outer space is a place you can point a telescope toward, but empty space is an idea physics has to define with much greater care. That difference sounds small until you begin to feel it, because in ordinary language we often use them as if they mean the same thing. Space is empty. Empty space is space, and the blackness beyond Earth must be the closest thing to nothing we can imagine. But they are not the same. Outer space is a region of the universe beyond Earth's thick atmosphere, where planets, moons, comets, dust, plasma, radiation, magnetic fields, gravity, starlight, and drifting atoms all share the same vast arena. Empty space, in physics, is not simply the place astronauts go. It is a more careful concept, a question about what remains when matter is removed as completely as possible from a region. And even then, the answer depends on what kind of emptiness you mean. Outer space is not empty in the strict sense. It only feels empty because its contents are spread across distances too large for human senses to grasp. Between Earth and the Moon, there are particles from the solar wind, traces of gas, micrometeoroids, electromagnetic radiation, and the constant influence of gravity. Between the planets, the Sun breathes outward a stream of charged particles that fills the solar system with a thin, restless environment. Between the stars, there is the interstellar medium, a faint mixture of atoms, molecules, dust grains, cosmic rays, magnetic fields, and radiation. Between galaxies, there is even thinner gas, often so sparse that a laboratory vacuum on Earth would seem crowded by comparison, yet still not absolutely empty. So outer space is not nothing. It is a real physical environment, just extremely thin, cold in many regions, harsh in others, and filled with forms of matter and energy that do not resemble the air-filled world your body evolved to understand. If you went into outer space without protection, you would not be entering a peaceful blank. You would be entering a dangerous environment where pressure is absent enough for body fluids to behave differently, where unfiltered sunlight can burn, where radiation can damage cells, where temperatures can swing depending on whether you face the sun or the dark, and where no air carries sound to your ears. The silence of outer space is not the silence of absolute nothing. It is the silence of no ordinary medium for sound waves to travel through. Light still travels. Radio waves still travel. Gravity still reaches. Particles still move. Instruments still detect. Outer space is silent to ears, but not silent to physics. This is the first major difference. Outer space is a location, while empty space is a condition. Outer space can contain stars, planets, spacecraft, dust clouds, radiation belts, nebulae, and galaxies. Empty space, depending on how carefully you define it, may mean a region with no air, no particles, no matter, or no detectable excitations of certain fields. A spacecraft can be in outer space while surrounded by radiation, solar particles, and debris. A laboratory chamber on Earth can contain a better vacuum, in one practical sense, than many regions of outer space, even though it is not outer space at all. This surprises people because we imagine space as the ultimate vacuum, but some parts of space are messy. Near Earth, the magnetosphere traps charged particles. Near a comet, gases and dust stream outward when sunlight heats the surface. Near a star, space can be full of plasma, powerful magnetic activity, and violent radiation. Inside a nebula, there may be clouds of gas and dust spread thinly across enormous distances. Beautiful in telescope images, but still much emptier than any cloud on Earth. Outer space is not one uniform darkness. It has weather, in a cosmic sense. Solar storms can disturb satellites. Charged particles can threaten astronauts. Dust grains moving at high speed can damage spacecraft. Gravity from planets and moons shapes trajectories. Space is not just an empty road. It is a landscape with invisible hazards. Empty space, by contrast, is often the idealized background physicists use when they want to study what happens without ordinary matter in the way. In a practical vacuum, engineers remove air so particles do not interfere with experiments or manufacturing. In particle accelerators, vacuum pipes are needed so beams can travel without constantly colliding with gas molecules. In astronomy, the near vacuum between worlds allows light from distant objects to reach us without being absorbed by thick atmosphere, though dust and gas still shape what we see in many places. But the deeper physics of empty space goes further than engineering. It asks whether a region with no ordinary particles still has fields, vacuum states, energy conditions, or gravitational meaning. That kind of empty space is not outer space as a destination. It is an attempt to understand the baseline state of reality itself. The second difference is scale. Outer space is everything beyond Earth's atmosphere, from the orbit of satellites to the space between galaxies. It includes crowded regions and sparse regions, bright regions and dark regions, violent regions and calm regions. Empty space is usually local and conceptual, a region considered as free as possible from matter or particles. You can ask whether the space inside a vacuum chamber is empty. You can ask whether the space between two galaxies is emptier. You can ask whether the quantum vacuum is empty in a more fundamental sense. But you would not usually say that a star-forming nebula is empty space just because it is in outer space. It is outer space, yes, but it is not empty in the physical sense that matters there. The third difference is emotional. Outer space looks empty because humans are not built to sense thinness across cosmic distances. If you could shrink the solar system into something small enough to hold in your imagination, the planets would be tiny islands scattered through a vast darkness, and the gaps would seem almost absurd. But those gaps still contain influence. Earth feels the sun's gravity across empty-looking distance. The sun's light crosses that distance and warms your face. Charged particles from solar eruptions can reach Earth and stir auroras near the poles. Cosmic rays from distant astrophysical events can strike the atmosphere. A space telescope can collect photons that have crossed billions of years. So outer space is not absence. It is connection stretched thin. Empty space, on the other hand, is the careful stripping away of contents until you are left asking what empty can mean when the stage, the fields, and the rules remain. This is where language becomes important. If someone says space is empty, you should ask, empty of what? Empty of breathable air? Yes, mostly. Empty of stars? Not everywhere. Empty of atoms? No. Empty of radiation? No. Empty of gravity? No. Empty of quantum fields? No, according to modern physics. Empty of meaning? Not at all. Outer space may be nearly empty compared with Earth's atmosphere, but it is not empty compared with absolute nothing. Even the best vacuum we can imagine inside the universe still belongs to the universe. It has location, it has time, it has physical laws, it can be crossed by light, it can be curved by gravity, it can be measured, That already makes it different from pure absence. This distinction matters because it prevents a simple mistake, thinking that the blackness between stars is the same as nothingness. It is not. The blackness is a region with a low density, not non-existence. The darkness is not a blank page outside reality. It is part of reality, carrying old light, weak particles, distant gravity, and the faint fingerprints of cosmic history. Outer space is not the opposite of the universe. It is most of the universe. The objects are rare. The distances dominate. The gaps are not failures of creation. They are the structure that lets galaxies form, planets orbit, light travel, and observers look back in time. If everything were packed tightly together, there would be no sky as you know it, no stable orbits, no quiet separation between stars, no cosmic history readable in ancient light. The emptiness of outer space is not useless. It is what gives the universe room to become legible. And yet, empty space as a physics concept reminds us not to stop there. Even when the visible contents are removed, even when outer space becomes unimaginably thin, the deeper question remains: what is the physical state of what is left? That is why this topic belongs in a series about the vacuum. It teaches the listener to separate the cinematic image from the scientific concept. Outer space is the black ocean around worlds. Empty space is the question of what remains when that ocean is drained of ordinary contents. Outer space can be mapped, traveled, orbited, measured by probes, photographed by telescopes. Empty space is defined by conditions, by what has been removed, by what still remains in the field description, by what the laws allow in the quietest possible state. One is a cosmic environment, the other is a physical idea. They overlap, but they are not identical. And maybe the most beautiful part is that both are humbling in different ways. Outer space humbles you with scale, showing that planets and people are small inside a vast, thin, ancient universe. Empty space humbles you with depth, showing that even when matter seems gone, reality may still have structure beneath appearances. One stretches the imagination outward, the other pulls it inward. Together, they teach you that emptiness is not simple. The dark between stars is not absolute nothing, and the vacuum of physics is not merely a place far from Earth. Why absolute nothing may be physically impossible? Absolute nothing may be impossible not because the universe is secretly hiding something inside it, but because the moment physics can talk about a condition, that condition has already become more than nothing. This is the strange trap at the center of the idea. You can imagine an empty room, but the room remains. You can imagine black space, but space remains. You can imagine silence, but the possibility of sound remains. You can imagine a universe with no stars, no atoms, no light, no dust, no motion, and no life. But if there is still a place where all of that is absent, then you have not imagined absolute nothing. You have imagined an empty somewhere, and absolute nothing would not be an empty somewhere. It would have nowhere. It would have no distance, no direction, no duration, no before, no after, no law, no field, no possibility, no observer, and not even a blankness waiting to be named. This is where physics becomes almost philosophical, but not in a careless way. Physics studies states of systems. It asks what exists, how it behaves, how it changes, what can be measured, what can influence what. But absolute nothing would not be a state of a system, because there would be no system. It would not be a vacuum, because a vacuum is still a physical condition. It would not be empty space, because space is already part of reality. It would not be a dark void, because a void still has the structure of being a void. Absolute nothing is not simply hard to find. It may not belong to the category of things physics can physically describe. And this is why saying it may be physically impossible is subtle. In normal speech, impossible means something cannot happen. But happen already assumes time. A thing that happens has a before and after. It takes place in some reality where change can occur. Absolute nothing has no time in which a happening could unfold, no laws to allow or forbid an event, no background in which a transition from nothing to something could be tracked. So if someone asks, could absolute nothing exist? The the question begins to bend under its own weight. To exist is already to be something. To be absolutely nothing is not to exist at all. That sounds like wordplay, but it points to a real difficulty. Physics cannot treat absolute nothing as a physical object sitting at the edge of the universe, because the edge, the universe, and the sitting would already be too much. Even the phrase "from nothing" is dangerous. If by nothing you mean a quantum vacuum, that is not absolute nothing. If you mean no particles, fields may remain. If you mean no classical space, perhaps some deeper quantum gravitational structure is being assumed. If you mean no laws at all, then there is no rule explaining why anything should appear, but also no rule preventing it. The language loses its grip. This does not mean scientists know why existence exists. They do not. Honest science does not pretend that the deepest question has been fully answered. But it does show that many versions of nothing used in physics are not the absolute nothing of philosophy. They are stripped down physical conditions. Low energy states, empty regions, absence of matter, early universe boundary conditions, quantum states without familiar space, or mathematical models where ordinary time behaves differently. These may be strange, profound, and important, but they are not pure non-being. They still contain structure. And structure is already something. There is another reason. Absolute nothing may be physically impossible. Physical reality, as we understand it, seems to be built from relationships. Space relates positions, time relates events, fields relate values across regions, forces relate particles and systems. Even measurement is a relationship between what is measured and what records it. Remove every relationship, and physics no longer has anything to describe. But if there is anything describable, even a boundary, a rule, a probability, a potential, then something remains. This is why absolute nothing is not like the number 0 in a calculation. 0 can sit inside a mathematical system. It has a place, a role, a meaning given by the other numbers around it. Absolute nothing would not even be 0, because 0 is already an idea inside a structure. A blank page is not nothing. It is a page. A silent note in music is not nothing. It is a pause inside a rhythm. A vacuum in science is not nothing. It is a physical state inside a theory. Every analogy eventually fails because every analogy gives nothing a home, and absolute nothing would have no home. The human mind struggles here because it evolved to subtract objects from scenes, not to subtract the scene itself. You can remove the tree from the field from the planet from space, and the stars from the sky, but your imagination keeps leaving a stage behind. It wants a darkness where nothing sits. It wants an emptiness that can be pictured, but anything you can picture is already not absolute nothing. This does not make the question meaningless. It makes the question revealing. It shows that existence may be more basic to thought than absence. Maybe the deepest mistake is imagining that nothing is the default and something is the problem. Perhaps nothing is not a natural default at all. Perhaps the idea of nothing only arises inside a universe where minds can compare presence and absence. A whole is only a whole because there is something around it. Silence is only silence because sound is possible. Empty is only empty because fullness can be imagined. Without a framework, absence has no contrast. So absolute nothing may be less like a hidden state the universe avoided, and more like a limit our language points toward but cannot physically reach. This does not prove that the universe had to exist, and it does not solve the mystery of why there is anything at all. It simply teaches caution. When we ask why there is something rather than nothing, we may be asking a question our words make sound clearer than it is. We may be comparing existence to an impossible alternative, a kind of absence that cannot be a physical option, because options require a space of possibility. And yet this realization does not drain the wonder, it deepens it. If absolute nothing cannot be physically defined, then the universe is not merely an object that appeared against a blank background. It is the background, the rules, the fields, the distances, the time, the possibility of questions, all arriving together in a way we still do not fully understand. You are not sitting inside a world that simply replaced nothing like a candle lighting a dark room. The room, the darkness, the candle, and the idea of replacement all belong to the world whose existence we are trying to explain. That is the quiet shock. Absolute nothing may be physically impossible, because physics begins only when there is enough reality for possibility, law, change, or meaning to exist. Before that, if before even applies, there is not a hidden emptiness waiting patiently. There is no waiting, no patience, no emptiness, no stage. And maybe that is why the question feels so endless. The deepest mystery may not be that something came from nothing, but that nothing may never have been a physical thing reality could become. The universe as excitations on invisible fields. The universe may not be made of things at all, but of invisible fields briefly rising into the things we mistake for the deepest layer of reality. This idea feels strange because your whole life trains you to trust objects. A cup sits on a table, a stone rests in your palm, a star shines in the distance. Your own body feels like a collection of parts with weight, shape, and edges, so it seems natural to imagine the universe as a vast inventory of objects, some large, some tiny, all placed inside space like furniture inside a room. But modern physics gradually turns this picture inside out. It suggests that what we call objects are not the primary ingredients. They are stable patterns, long-lived arrangements, visible consequences of something more basic. Beneath the familiar world of matter and light, physics describes fields that extend through space, and what we call particles are excitations of those fields. An electron is not best understood as a tiny solid bead hiding somewhere inside the atom. A photon is not simply a miniature glowing pellet flying through darkness. They are events in fields, local disturbances carrying energy, charge, spin, and other properties in ways that instruments can detect. The field is the deeper presence. The particle is the moment it becomes countable. And if you let that idea expand, it changes the entire universe. Stars become not merely balls of gas, but enormous organized processes where fields and particles exchange energy under gravity. Atoms become not miniature solar systems, but stable quantum arrangements in which fields form patterns that can persist. Your body becomes not a pile of hard microscopic material, but a living architecture built from field excitations arranged into atoms, molecules, cells, signals, and memory. This does not make anything less real. It makes reality less like a warehouse and more like a song. A note is real, but it is not separate from the vibration that produces it. A wave is real, but it is not separate from the system in which it moves. A flame is real, but it is a process, not a solid object. In a similar way, the world you touch may be real as pattern, real as structure, real as interaction, without being made from ultimate little chunks of solid stuff. This is where the phrase, "the universe as excitations on invisible fields," becomes more than a dramatic title. It is a way of seeing matter as activity rather than substance. It says that the visible world is the field world in motion, organized enough to appear as particles, then atoms, then chemistry, then planets, then organisms, then thought. The field itself is not visible in the ordinary way because your eyes evolved to respond to light, not to the full hidden machinery behind light. You do not see the electron field spread through space. You see the consequences of electrons in matter, electricity, chemistry, and the glow of screens. You do not see the quark and gluon fields directly. You see protons and neutrons, atomic nuclei, the mass of ordinary matter, the stability of the world. You do not see the Higgs field as a color or mist, but the masses of certain particles carry its quiet signature. The universe is full of these unseen layers, not as fantasy, not as mystical energy, but as the serious language of quantum field theory. What makes this powerful is that fields are not just labels for particles we already knew. They reshape what we mean by existence. In the old picture, a particle could be imagined as a permanent tiny object moving from place to place. In the field picture, the same kind of particle appearing anywhere in the universe is an excitation of the same kind of field. This helps explain why electrons everywhere have identical properties. The electron in your body, and an electron in a distant nebula are not similar because nature copied a design badly or well. They are excitations of the same universal field, following the same rules. Identity comes from the field, not from little individual craftsmanship. That is a quiet revolution. The sameness of particles across the cosmos is not boring repetition. It is evidence that the deep structure of reality is shared everywhere we can observe. When the early universe was extremely hot and dense, fields were not arranged into the calm, familiar forms you see now. As the universe expanded and cooled, particles formed, symmetries changed, stable matter emerged, and eventually atoms could hold together. Later, gravity gathered gas into the first stars. Those stars forged heavier elements. Supernovae and stellar winds spread those elements into space. New stars and planets formed from enriched clouds. Chemistry became richer. On at least one world, molecules arranged themselves into life. But through all those stages, the deeper story is not stuff becoming more stuff. It is fields forming excitations. Excitations forming stable systems. Stable systems producing complexity, and complexity eventually becoming aware enough to ask what it is made of. This is not a reduction of meaning. It is an expansion of meaning. You are not less astonishing because you can be described physically. You are more astonishing because the same universe that began as hot fields and particles could, across time, arrange itself into a nervous system capable of understanding fields and particles. Yet we must be careful not to turn this into a vague claim that everything is energy in the loose popular sense. That phrase often hides more than it reveals. The real physics is more disciplined. Different fields have different properties. Different excitations behave in different ways. Matter is not interchangeable with emotion, and quantum fields do not mean thoughts magically rewrite the cosmos. The wonder is not that anything can mean anything. The wonder is that specific invisible fields, following specific rules, can produce a universe as rich as this one. Electromagnetic fields allow light, chemistry, and the behavior of charged particles. Strong force fields bind quarks into protons and neutrons. Weak interactions allow certain kinds of particle transformations important in stars and radioactive processes. The Higgs field helps set the masses of certain fundamental particles. Gravity, described most successfully by curved spacetime rather than a quantum field in the same complete way, shapes the large-scale architecture of the cosmos. We do not yet have a final theory uniting all of this, especially gravity with quantum mechanics, so the picture is powerful but not finished. That incompleteness matters. Honest science does not pretend the final page has been written, but even the current picture is enough to transform ordinary perception. Look at your hand. It seems solid, continuous, simple, but inside it are atoms held by electromagnetic forces, nuclei whose mass mostly comes from strong field energy, electrons arranged in quantum states, photons constantly exchanged in interactions, molecules vibrating and folding, cells using chemical gradients and electric signals. What appears as one hand is an organized symphony of field behavior. Look at the night sky. Each star is a gravitationally bound furnace where matter and radiation interact under extreme conditions. Each beam of starlight reaching you is an excitation of the electromagnetic field that may have traveled for years, centuries, or millions of years before meeting the chemistry of your eye. Look at darkness itself. It may contain no visible object, yet the field framework remains, allowing future particles, radiation, and interactions to be described. The universe is not a stage populated by final objects. It is a layered activity where the visible is the crest of the invisible. And perhaps this is why the idea feels so strangely calming. It dissolves the hard loneliness of objects. Nothing stands completely alone in the deepest description. Every particle belongs to a field. Every atom belongs to interactions. Every body belongs to chemistry, gravity, history, and light. The borders you see are real at your scale, but they are not the final truth. A wave has a shape, but it is not separate from the ocean. A word has meaning, but it is not separate from language. A person has identity, but even that identity is carried by patterns, memory, matter, and time. Physics does not erase the person. It shows the hidden continuity beneath the person. Still, this continuity should not be confused with mystical oneness. A chair is not the same as a star. A thought is not the same as an electron. Differences matter. Structures matter. Scale matters. The point is not that all things blur into one vague substance, but that all things may arise from deeper fields whose excitations and interactions create the diversity of the world. That is more precise and more beautiful than a simple slogan. It says the universe is not built from dead parts, but from active principles. Not from ultimate hardness, but from stable patterns. Not from visible surfaces alone, but from invisible fields made manifest. And maybe the deepest shift is this. In the field view, reality is less noun and more verb. A particle happens, a force relates, a field changes, a star burns, a body metabolizes, a brain predicts, a mind wanders. The world is not a frozen collection of things, but an unfolding of processes stable enough to be named. You are one of those names, one of those patterns, one of those long-lived arrangements of field excitations that learn to breathe, remember, fear, love, and look back at the universe with questions. So when you hear that the universe may be excitations on invisible fields, do not imagine a ghostly illusion or a fake reality behind the real one. Imagine the familiar world becoming deeper, the solid becoming structured, the visible becoming the surface of a hidden order. Why the quietest place in reality is still full of activity. If you could turn the volume of the universe all the way down, past the hum of atoms, past the glow of stars, past the last drifting particle, you might expect to find pure stillness waiting at the bottom. But physics says the bottom is not silent in the way your senses imagine. The quietest place in reality is not a dead emptiness, not a cosmic pause where existence has finally stopped, but a deeper kind of calm where activity continues without becoming obvious. This is difficult to feel because your body was built to notice movement, heat, pressure, color, sound, and touch. If nothing presses against your skin, you call it empty. If nothing reaches your ears, you call it silent. If nothing shines before your eyes, you call it dark. But the universe is not limited to the signals your body can receive. Beneath ordinary perception, even the most carefully emptied region still belongs to a physical world made of fields, laws, possible states, and subtle relationships. A vacuum is not absolute nothing. It is the lowest available state of the fields under certain conditions. And lowest does not mean erased. It means quiet in the physical sense, not non-existent in the philosophical sense. That difference matters because it changes the meaning of stillness. In classical imagination, if you remove all particles from a space, the story ends. Nothing remains to act. Nothing remains to change. Nothing remains to matter. But in quantum physics, removing particles does not remove the fields from which particles can arise, nor does it remove the rules that shape how those fields behave. The vacuum is like a perfectly dark theater before the performance begins. Except even that metaphor is too simple, because the theater itself has shape, acoustics, wiring, tension, and hidden structure. The darkness is not the absence of everything. It is the absence of visible action. In the same way, the quantum vacuum is not crowded with ordinary objects, but it is not a blank failure of reality. It has fluctuations, correlations, and measurable consequences. These are not magical bubbles of matter constantly popping into existence in the crude way popular images sometimes suggest. They are more subtle than that. Unavoidable quantum behavior in fields that do not become perfectly sharp, perfectly fixed, or perfectly dead. The vacuum can influence the energy of atoms by tiny amounts. It can help explain small shifts in spectral lines. It can contribute to forces between surfaces placed extremely close together. It can define the environment into which excited atoms release light. It can respond differently near boundaries, intense fields, curved space-time, or horizons. None of these effects are loud. None of them look like sparks in the dark. But science does not require something to be loud before it becomes real. Some of the most important truths in physics are discovered only when instruments become patient enough to measure what human senses dismiss as nothing. Think of the difference between a still lake and a frozen photograph. From far away, both may look motionless, but the lake is a physical system, holding depth, pressure, temperature, and the possibility of waves. A photograph only represents stillness. The lake contains it. The vacuum is more like the lake than the photograph. It can be in its lowest state and still retain a hidden structure. It can appear empty and still set the stage for light, matter, and interaction. It can be quiet and still have a kind of physical grammar. This grammar is what allows particles to have meaning when they appear. A photon is not a glowing marble traveling through dead nothing. It is an excitation of the electromagnetic field. An electron is not a tiny bead sitting on top of emptiness. It is tied to an underlying electron field. Other particles have their own field descriptions. The visible universe is not built on a blank floor, but on a layered field reality that remains even when nothing visible is happening. That is why the quietest place is still full of activity. Because the activity is not always the movement of things, but the persistence of conditions. It is the quiet availability of allowed patterns. It is the structure that says what can happen before anything happens. It is the hidden order that makes future events possible. This also helps explain why emptiness matters on cosmic scales. The space between galaxies may look like a vast absence, but the expansion of the universe suggests that empty space itself may carry properties that influence the fate of everything. Dark energy, whatever its true nature turns out to be, behaves as if the emptiness between galaxy clusters is not just a passive gap. It seems connected to the accelerating expansion of the cosmos. And although we do not yet know whether dark energy is truly vacuum energy, a changing field, or a sign of deeper gravitational physics, the lesson remains powerful. The quietest regions may shape the largest future. The universe may not be guided only by stars, black holes, and glowing matter, but by the almost invisible behavior of the spaces between them. Still, we must keep the wonder honest. The vacuum is not conscious. It does not breathe, think, desire, or secretly create with intention. It is not alive in the biological sense, and it is not a mystical force waiting to be harvested as unlimited power. Its activity is physical, constrained, and described by theories that have to answer to experiment. That honesty makes the idea stronger, not weaker. The real vacuum does not need exaggeration to be astonishing. It is already strange enough that a region with no ordinary particles can still have field structure. It is already strange enough that the lowest state of a system can still have consequences. It is already strange enough that what looks like nothing can help determine atomic behavior, cosmic expansion, and the deep stability of matter. And perhaps this is why the topic feels so reflective. It mirrors something you may already sense in life. Quiet is not always absence. A sleeping city still has electricity moving through walls. A calm face can hide 1,000 thoughts. A seed in dark soil can look dead while holding the pattern of a forest. A silent room can contain memory, expectation, and the weight of things unsaid. Physics does not turn these into scientific claims about emotion, but it gives them a strange resonance. It reminds you that the visible surface is rarely the whole truth. The universe often works beneath notice, building its most important structures in layers too subtle for immediate perception. So when you imagine the quietest place in reality, do not imagine a final emptiness where existence has failed. Imagine a depth where the obvious has been removed, leaving the hidden framework exposed. Fields in their lowest states, space-time holding geometry, laws preserving possibility, and subtle effects waiting for the right conditions to become measurable. The quietest place is still full of activity because reality itself is not made only of objects. It is made of relations, constraints, states, fields, and possibilities that remain when objects disappear. And maybe that is the final lesson of the vacuum. The universe does not need noise to be profound. It does not need brightness to be present. It does not need visible motion to be active. Beneath the stillness, beneath the darkness, beneath the silence your senses call empty, there is a deeper order holding everything open, the quiet machinery of existence, working without applause, shaping the world before the world becomes visible.